So good morning, everybody. Welcome for this second day of the school, The Mathematics of Machine Learning. It's a pleasure to introduce this morning Professor Simone Di Marino, who is an associate professor at the University of Genova and is the true organizer of the school together with Augusto Gerolin. So he did many things in his life. During this course, he will talk about optimal transport and with some applications to machine learning.
Okay, can you hear me? Okay, so first of all, probably some things will be a bit technical, so please interrupt me at any time if you feel lost or if you don't know something. We will begin by really preliminaries. So there will be preliminaries in measure theory because maybe not all of you know the theorem that then we will use. So our main object will be measures, right? So optimal transport. So optimal. The main characters in optimal transport are really measures. So we will fix fixing the notation. Mu will be a measure on the space X, and we can have additional measures which usually will be of the form of nu, which instead will be on the space Y. So we will have two main spaces, X and Y, and usually these spaces are just complete metric spaces. Complete metric spaces, and we take measures with the sigma algebra, which is the Borel one. So we have a topology here inherited from the metric structure. And so with the open sets, we generate a sigma algebra, which is the one of the Borel sets. So we can talk about these measures. And optimal transport is a general theory, which we will see it does not only deal with transporting stuff, but in general, do couplings, we will have some optimization of costs. But the main thing is that we will have measures and a coupling between those measures. We'll see later. So in these spaces, the space of measures, they have a topology. What do I mean by a topology? So a notion of convergence in the space of measures, right? So this notion of convergence that we will use is the weak star convergence. So we will say that mu n converges weakly to mu. So those are all measures in the space of positive measures on X. If the following holds, so when I do the integration of a continuous function with respect to mu n, this will converge to phi x d mu. Okay, so if you wish, this is a convergence in expectation, where the expectation we are taking the expectation of phi with respect to mu n and with respect to mu, right? So this notion of convergence is called weak convergence, because if you think of mu n or mu as having densities, this convergence is much weaker than the convergence that you would take maybe as L1 convergence or pointwise convergence or something like that. So, as an example, which we'll see immediately the geometric character of this type of convergence, is that if you take, for example, mu n, which is the delta Dirac on point xn, and mu, which is the delta Dirac on point x. Now, if you take any kind of norm that you imagine on the space of measures, the difference between mu n and mu we'll have a norm which is 2 or something like that. And instead, what happens if I take, so this should hold for every phi, which is continuous and bounded functions. Now, if phi is continuous and bounded, what do we have? We have that integral of phi with respect to mu n. This is just phi of xn. And now if we have that xn is converging to x with respect to the metric d that we have on the metric space, since the function is continuous, then phi of xn is converging to phi of x, right? So this is the main property, if you want, of the weak convergence. It is a geometric convergence in the sense that if you take a delta peak and the delta peak is moving in the space, then this converging is catching really this convergence in the space, which does not happen for L1, for total variation, or other kind of distances that you can think. Okay, and so this will be the convergence that we usually use, this topology that we use on the set of measures, and we have a nice characterization of compact sets in this topology, and this is called Prokhorov theorem. So Prokhorov theorem says that tau, a subset of the set of measures, is compact in the weak topology if and only if two conditions have to be satisfied. So tau is closed under weak convergence. So of course, any compact set should be closed. And the other condition is that for every epsilon, there should exist k epsilon, which does depend possibly on tau, but not on the measure mu, such that the measure of the whole space minus the compact set is less than epsilon, right? So we have the set X, and we are saying this set is compact if there exists for every epsilon a compact set, such that outside of these compact sets, every measure in my tau charges less than epsilon, right? Has mass less than epsilon. Okay, and it should be also bounded. Maybe I should write it somewhere. And it's bounded. Yes. Yes. These yeah, I call it star, but yeah, weak star, yes. Weak star and weak star. So this is my definition of weak. Because sometimes there is, yes, the difference between weak star and weak if is that here we have continuous and bounded, or continuous and zero outside a bounded set or something like that. And so there is a difference, for example, in Rn, but we will work with this one, and with this one we need this tightness. This is sometimes called tight, so it's called tightness. So we say that the set tau is tight if for every epsilon it happens this. So This is the main condition one has to have. Then the other two are obliged because you need to be closed and you need to be bounded. Okay, so this is about the topology and the convergence that we'll use in the measure spaces, in spaces of measures. And then we'll talk about the push forward, which is a way of producing measures in the second space starting from measure in the first space. So definition, push forward. Even mu in the measures of x and t a map from x to y, Borel. We define the following measure, which we'll be calling t sharp mu, which has to be read as this is the push forward of mu with respect to the map T. So this will be a measure on Y, right? So we have to specify the weight of a set with respect to this measure. So what is the mass of a set A subset of Y? This is simply mu of the pre-image of A. Now these, yes? Yes, so A Borel. Sorry. Yes, for every A, which is Borel. Because in such a way, T minus 1 of A is still Borel because T is Borel, so is measurable here. And so we can, sorry, the opposite. If A is Borel, then T minus 1 of A is Borel as well. And so mu of T minus 1 of A makes sense. So this definition can be intimidating at first, but it's really what we want to do, thinking really of transporting a measure. So we are moving the mass according to the map T. So the idea is that we have this space X and this space Y. Here we have some distribution of mass according to mu, and we are transporting to the map T, right? So we ask ourselves, so how much mass has gone into the set A? Well, we look at every particle that goes in A. What is every particle which goes in A? Is precisely the set T minus 1 of A, right? So this set is T minus 1 of A. This is precisely all the particles that will go into this set, right? And so precisely we say, okay, what is the mass charged by A? Is precisely the mass that we had here, right? So this is precisely the notion that that allows us to say, okay, this is a way of transporting the measure mu into another measure on Y. What is this measure? It's the measure defined by this. And another way, equivalently, we have an equivalent formulation, which is usual in the setting of measures. So if we have a definition based on sets, we have also a definition based on functions, and they are the same. They are equivalent. So what is the definition based on functions is that if we do the integral of phi of y with respect to this measure, so the idea is that another way of specifying what is this measure is saying what happens to this measure if I integrate it with respect to a function. If I know this for every function, then I can say what is this measure, right? And what is this? This is just the most natural thing that you can put here. So integral with respect to x of phi of t of x with respect to d mu. So this is a measure on y, remember, and this is a measure of x, right? So if you want, this is a general implicit rule for the change of variable formula, right? So because here, if you see it like this is something like, okay, this is phi composition with t. I want to write it as an integral of phi of y, so I put t of x equals to y, and I want to do a change of variable formula, right? So this t sharp mu is encoding all the derivatives, if you want, in the change of variable formula. But this is more abstract and more powerful, if you want. More powerful because it works for every Borel map T, not just for differentiable ones, and it works on every space. Here you don't need x and y to be RD, right? So if you want, this is a generalization of the change of variable formula. What is the drawback? The drawback is that this is not readily computable. You don't have a formula for it, right? The formula is precisely this one. So this is a way, this is the only general way to say what is this this measure. You don't have a pointwise formula in general. Okay. So once we have this, we can actually state the first version of our optimal transport problem. And the first version is the is really the first historical version, which is the one due to Monge. So up to now, we just have maps, have a map which is transporting a measure mu to a measure, to another measure, which is t sharp of mu. And now the idea is that we really want to, maybe I do the drawing here. So the problem of Monge was really that of transporting in the real sense of the labor work stuff. In this case, it was soil. The idea is you wanted to dig up a hole, right, which was prescribed. So I have to dig a hole here in this shape, and then I want to use the soil to, oh yeah, we have color chalks. So this is our hole that we want to make. And then with this soil, we want to build some walls, because again, mathematics in the 1700s was usually make to be better at war, and this was because, okay, you have to build stuff to be defensive with respect to the attack of the enemies, and so you want to do it in a way which is the most economical one for the labor work, right? So, for example, in this case, you would say, okay, this part of the soil should go here, and this part of the soil should go there, right? And what is the most economical way? Probably this place, which is the most, the rightmost one, should go there, and etc. So these should go there. I don't know. So you can imagine what is the best way. So, and this best way, you want to find it, and so your goal is to find this map T, which transports this soil from this well to build these two walls, right? And so what is mathematically the objective? So you say that this, yeah. So this shape here will be our mu. So the measure really, which is in this case is really the mass of the soil. which is the starting measure, and you want to build this transport map, which maps to measure nu, which is prescribed, which is your walls. So our Monge problem is given mu in, and now here we will normalize. We will have always probabilities. Probability, because of course here you should have the same mass here and the same mass there. You don't want to have less mass here, of course, and you don't want to waste soil from here. And you can normalize once you have fixed the mass. You can normalize. So fixing mu and nu. What you want to find is the infimum of what? What is the cost? So for every little piece of mass here, what you want to pay is actually, okay, this mass here, which will be our d mu of x, times the distance that I have to make, because the work is proportional to the distance, right? Now, what is the distance from this point to this point? Now, this will be t of x minus x. So the distance really that we traveled with the modulus. So this is the original problem of Monge. So you take just the Euclidean distance, and this is, of course, on omega, which is, and x is Rd in this case, and y is the same Rd. So this is a very particular setting, if you want, because the spaces are the same. And you want to minimize this cost, this is the transportation cost, this total transportation cost, among all those T transport map between mu and nu, which is to say, so this is the same as saying nu equals T sharp mu. Right? So T being a transport map from, from mu to nu, is precisely saying that, as we explained here, nu should be equal to the push forward of mu through T. Okay. So now this is what we will call the Monge problem. Sometimes we will say just M. Okay, so some comments are in order now, because there are several problems with this problem. The idea is that, again, we want to find the infimum, so we want to minimize. We have to minimize with respect to what? With respect to T. So first of all, we have to consider what is the set of transport maps, right? And the set of transport maps, now if you see what is the condition is highly nonlinear with respect to T. As Ernesto was saying yesterday, it would be very nice to have convex problems. This is not at all convex, even though the functional maybe is convex with respect to T, but if the functional is convex, but the constraint is not convex, it's like, okay, yes, I have a linear function, but I'm minimizing on a stuff like this. So it's still super nonlinear, super non-convex to minimize something on a set which is nonlinear. But more importantly, it can be, so the remarks are that the set of transport maps can be empty. And this is the biggest problem, if you wish. So we are minimizing among things that maybe do not exist. And so this problem immediately doesn't make sense. And what is the example? Well, the example is simply you take mu, which is the delta in one point, and you take nu, which is 1/2 the delta at y1 plus the delta in y2. So why is that? Because if you transport a delta measure, what you obtain, if you have just a delta measure here, when you transport it, what you obtain? You obtain another delta measure in what point? In t of x, right? So the transported the transported measure of delta in x is just delta in t of x. And so in particular, it cannot be that delta of t of x is equal to 1/2 of one delta and another delta, right? So in other words, with this formulation, we cannot split the mass, right? What we want to do here is to say, yeah, okay, 1/2 of the mass goes here and 1/2 of the mass goes there, which in this scenario, it kind of makes sense, right? So you imagine here, there will be this line here that, okay, sometimes I will go here, sometimes I will go there, right? But if you think of really the grain of sand or something like that, then this grain of sand, I cannot divide it. It should go one place or another. So we cannot do it if you're dealing with the delta measures. And the other problem is that even though the set of transport maps is not empty, the infimum sometimes cannot be reached. What do I mean? I mean that here I'm doing the infimum, and as you know in analysis in general, if you take, for example, I don't know, f of x, which is 1/1 plus x squared, this is a very nice function. What is the infimum of this function on the real line? It's 0. Is it attained? No, because I should go to infinity, but infinity is not allowed by the problem in some sense. And here it happens something similar, and it's always a case of that I cannot split the mass, basically. I won't do the example. I won't do the example in a formal manner, but let me draw the picture. So the picture is that mu is equal to a mass concentrated on a line, and nu is the mass concentrated on two lines. And here I have double the density, right? Now I want to transport these to the union of these guys, right? So as I was picturing here, some particles should go left and some particles should go right, right? But now if I have only a map, well, these there will be a set which goes here, there will be a set which goes there, there will be a set which goes here, but the idea is that as long as I have a map, some of those arrows will be a bit slanted, right? I cannot be just horizontal everywhere, because otherwise I'm mapping this guy to double the density here, and I will have holes and stuff like that. So it cannot be that I really split the particles, but the infimum is attained because the infimum, it will be something like, okay, I have to split the mass really, and the way that I can do it, approximate at least the optimum, is to divide it in many things, and then say, and I divide these other ones in double the number, sorry, in half the number of of pieces. Then I say, okay, the first half here will go here, will go to the left, and these will go on the right. These will go on the left, and these will go on the right. And now when I do this, I see that all my arrows are nearly horizontal. In the limit as the subdivision goes to infinity, I will have the cost which is as going horizontal, but I cannot reach the optimal cost. The only way to reach it is really by splitting the particles. In every point, I should go half of the mass should go here and half should go there, which again is not possible because of this. Okay. How to solve this? So we will come back to how to solve this, but I will do an excursus which motivates a more general way of dealing with this, which I'll try to let it come up in the most natural way. So for a moment, we pause the general measure setting, and we pass to the discrete, because in the discrete it's more natural to see this next formulation, which is the Kantorovich formulation. So and here we will talk about matching, which is again similar. So you will see that there is a comparison. So now I take basically X, which is just a discrete set, X1, Xn, and Y, which is again a discrete set with the same number really. And now in this setting, these will represent the workers. So these are workers that wants to find a job, basically, looking for a job. And these are factories looking for a worker. Okay. And now what I want to do, I want to match those up in the best possible way. What does it mean in the best possible way? I want to minimize something, and this something will be a cost. So I will have a cost, general cost, usually just 0 plus infinity. It can be also plus infinity, but we don't care. And the idea is that the lower cost means better matching. So this is what it is a function which takes a worker and a factory, and it gives me a number, right? What could it be? So the idea is that we want to quantify how well a factory and a worker could be together, right? So if we have, the idea is that everyone has a curriculum, has some preferences, and every factory has a job opening which has some requirements, right? And so this cost, in some sense, is a way of quantifying how well they match in this sense, right? So why we want to do that? Because we want to quantify what is the best matching. In order to quantify, we want to understand what does it mean to have a matching which is better than another. And again, in the same spirit that Ernesto did yesterday, we try to do a linear thing, which is the first basic thing that we want to do, a linear thing, and just an ordering in the real number. So for each for each matching, I will give you a real number, and this ordering will be just, okay, if I have a number which is higher or lower, then this means that the matching is better or worse. So what are the matching? Just permutations. Because at every worker I should say, okay, in which factory should it go? In the factory sigma of I, where sigma is a permutation. Because I have n factories and n workers. So what I want to do is to find the infimum among, and this is really a minimum because it's a discrete set, sigma in Sn of what? I just do the sum of these costs. So I just goes from 1 to n of the costs, C of xi, y of sigma I. Right? So these are all the possible matchings, and I'm looking for the best matching in terms of the cost, the total cost that I have, right? You may think that in this setting, this is just an arbitrary way to choosing the best matching, but again, is the maybe simpler way, simplest way that that we can think of by optimizing globally this kind of stuff. Okay, and this again is very similar to doing the transport map, right? Because in some sense, this sigma is none other than the map that goes from the workers to the factories. And is, of course, in some sense, preserving the measure, in the sense that if I take the uniform measure here and I do the permutation, I get again the uniform measure. And here I'm minimizing among the maps, which is the natural thing to do. But now I just tweak just a bit the setting in a way that in some sense is more transparent and what you actually want to do, because you don't want really what you do in the end when you are doing this cost is not really impairing the person to the factory, right? What we said is really we take the curriculum and the requirement of the jobs. So if you want what really you are doing, you take x, which is again x1, xn, and now y, which is y1, ym, with these two numbers which are different. So, and these are now the type of workers, and this is the type of factories. What do I mean by that? In some sense, I'm taking just the relevant features that I want. Maybe here I just want, I don't know, the vote of the degree. And I don't know, the number of years that he has worked in that particular field. And here I want just the salary and the degree of specialization which is needed for that job. And then I want to pair these numbers. So I don't have anymore a personal preference, but now I have type of workers and type of factories. And now the measure makes much more sense. What is the role of the measure? So the measure will be played by the number of type of workers that I have. So I have Ni, which is the number of workers of type A, type I, and Mj, which is the number of job of a factory jobs of type J. And again, I want this kind of equilibrium condition, sum over I of Ni, which is equal to n, sum over J of Mj. So the number of people that I want to place is equal to the number of jobs that I have available. This is again in the simple setting. You can have also M, which is bigger than n, and n is, but it's a bit more complicated with just use the simplified setting. Okay, now what is the measure if you want? So the measure that we are considering is just the measure associated with this number of workers. So it's just the sum of, so every time that I have a worker of type A, I put a delta on xi. So I have delta of xi times ni. And then I want to normalize in such a way that this is a probability measure. So I have to divide by the number of workers, which is n. So divided by n, and nu will be just sum of mj over, again, n, which is equal to m, delta of yj. Okay, but now in this case, what I want to do is not really doing, so the type of worker xi goes here or goes there. Now it's more of a table, right? So it's more of a table where I have x1, xn, yn, ym. And now in this table, what should I put? In this table, should I put some number, gamma ij? This gamma ij is what? What is the number of people of type A, which I will place in the job of type J. Number of workers of type I, which to a factory of type J, right? And so this gamma, which is this matrix gamma ij, now this will be a planning, if you want, planning. And a planning that I make in order to, okay, I want to put this number of people of this type to this factory and so on and so forth. And again, what I want to do is among the planning, I want to minimize the cost. But now there is a condition of this kind of planning, of course, right? Because I have a fixed number of people of type A, a fixed number of factories of type J. So what do I want? I want that this column, when I sum up all the gamma ij, I get precisely ni, right? So the sum of gamma ij on I must be equal to ni. Again, I'm normalizing, so this is divided by n. This is proportional to. And the same way here. So if I sum up, so this is sum in J, and if I do the sum in I should get mj divided by n. Right? So this is the condition, and actually this set, so gamma ij such that sum over I of gamma ij is equal to this mj divided by n, and sum of gamma ij is equal to nj and I divided by n. This is called pi of mu nu, which has the coupling or the plans between these two measures. So given these two measures, this is the way that I can couple these two measures, right? And now what I want to minimize, let me write it here. And this is the Kantorovich formulation. Kantorovich formulation. I want to minimize what? The sum over I and j of gamma ij, the cost of xi yj. Again, the linear cost, where gamma belongs to this pi of mu nu. Okay. Why this is a generalization? Because now if you think of this one, now if I put 1 over n here, now this kind of coupling, this kind of map, can be seen as just, you take the square matrix, which has entries which has just or either 0 or 1 over n. And I have in every row, I have every 0 and 1 over n, and the other ones accordingly. So the permutation matrix, related to the to that permutation. Okay. So is everything good up to now? Okay. And now we jump to the Kantorovich formulation in the continuous case, in the non-discrete case. So let me see if I said everything. Okay. And the important thing, of course, is that in this case, as we said, we cannot have splitting of mass in the sense that every worker of type A, I, should go to the same factory. Instead, this is not a constraint anymore. I can have that the worker of type I here can go to multiple different factories. But of course, we have several people of type I, so we will choose at random, basically, who will go here or will go there. So now, let me write this Kantorovich formulation. Kantorovich in continuous case. So in continuous case, we just replace everything with continuous stuff. So what is, we have to find the minimum of what? Now we have to do the integral. And now this is sum over I and j. So the integral will be over the product space x times y of what? D gamma, and this is on the product space. Now we'll say what are these things, and here I can have now a general cost. I hope that now you are convinced that we don't have to restrict ourselves to just Euclidean costs, but it makes sense to take a general cost from x and y. So I want to minimize this, where gamma now is a measure, it's a probability measure actually, on the space, on the product space, and gamma is a planning between mu and nu. And now I will say what is a planning between mu and nu. Now we have the space x here and the space y here. So this is the product space. And so you have a gamma, which is here. Now you have to imagine that is a density, is a measure on the product space, is a way to assign mass to x and y. And the idea is that if I take now gamma of A times B, is what? This is the mass that I will transport. Let me write it in parentheses, transport from A to B. So how much mass I will transport precisely from the set A to the set B. And this is what gamma will represent, right? So this is the meaning. And now, what is this condition? Well, if this is the mass that I have to transport from A to B, now if I take all this guy here, so gamma of A times Y, this is the mass that I have to transport from A to whatever to whatever point, right? So it's every point that I have in A. So this should be my starting measure, right? How much I transfer from A to everything is basically how much mass I have in A, right? So, and this is the first marginal constraint. And the same way should happen in the other side. So if I take X times B, this should be nu of B. And this is the second marginal constraint. Okay. There is another way to say it. So as I'll say it in another two ways, because maybe they will pop up these other equivalent definition in the following lectures. So this is, if you wish, in order to understand what is happening, but this can be seen also as so if you define pi x, which is just the projection on the first coordinate. So if I take a point xy and this pi of x is just the projection on the first coordinate, then this is equivalent to saying that if I do the push forward of gamma with respect to this projection, this is precisely mu. And the same with the projection on the second coordinate. This is the same as saying this. So this, of course, is for every A which is Borel. This is for every B which is Borel. Okay. And another equivalent way, which is the one that Ernesto said yesterday, because yesterday we saw already something like this, right? So we had this measure rho on the space x times y, and then we have rho x, which is the first marginal, so the distribution of the data points in x, right? And then we didn't mention it, but there is also rho y, which is the distribution of labels agnostically to the data. And so, and this is exactly what the relation. So pi of x of rho of yesterday is equal to rho x. This is precisely the same thing that we are doing. And the other thing that was said yesterday was, okay, if I do the integration with respect to just a function of one variable, with respect to the gamma, this should be doing the integration with respect to the first marginal. So in this case, the mu on x. Again, this is the same. This is for every phi which is CBX. This is the same as this, which is the same as this. They are all the same thing, and they are saying, okay, the first marginal is this one. And it is the same as saying, okay, if I do the sum column-wise, I get the distribution that I fixed a priori. Okay, so, yes. Here a minimum. And now the next step is to prove that this is a minimum. Because as we said, so in the Monge formulation, we had these problems, right? These two problems that the set on which we were doing the minimum can be empty, and the minimum in the infimum, it might be that it is not obtained. And the really nice thing here is that this doesn't happen anymore. So this will be now the brief theorem that I will say. Okay, and The same thing we could do it, of course, also in finite dimension. So in the discrete case, I didn't say it, but in the discrete case, of course, everything is discrete, and since gamma ij are greater or equal than 0 and their sum is 1, we are doing an infimum over a compact set in R something, in R n times n. I don't remember now the what was the in R times n. Yeah, n times R n times n. We are in a compact set, and so of course it's a linear function which is continuous. We are minimizing, so of course there is a minimum, right? So in this case, it's not obvious that there is a minimum. It's not either obvious that there is a gamma which works, right? So this is true also in the discrete case. It's not obvious that there is a gamma that works. Now, what is the gamma that works? So first point, pi mu nu is different from the empty set because mu times nu belongs to this guy here. So this is the product measure. The product measure, if you want, is a very stupid way of doing a coupling, which is saying basically, okay, I distribute them independently. So I pick at random a worker, and I pick at random a factory, and I put them and I couple them. Of course, this is not optimal. This will never be optimal. But the nice thing is that now we have a non-empty set, which is very nice. And the second point is now that there exists a minimum. So let me put this as a theorem. So there exists a minimizer. Sorry. Let me write some hypothesis because otherwise it's false. So what hypothesis we could make? So actually, we don't have to make hypothesis on mu and nu, but we have to make hypothesis on the cost function, which is the other variable that we didn't mention, if you want. And this cost function should play well, basically, with the topology of the space, because we said we are playing with the narrow convergence, so the important thing is the topology of the space. So actually here we will assume that C is continuous and bounded, which may be restrictive, but actually with the little work, we can generalize this to C, which is lower semi-continuous. But I won't speak about that because maybe you don't know what is lower semi-continuous, and in approximation procedures, maybe we will do it tomorrow. But for now, we fix the simple case, and then maybe tomorrow we will do the more general case. So this is our only hypothesis that we need. And then so mu probability measure, mu probability measure. Then there exists a minimizer gamma star of problem K. Not necessarily unique. Now here the linear structure plays a role, but sorry, it will play a role. So from the general point of view, not in the proof, because again, another thing which is interesting, which I didn't say, is that this is a convex space. So if I have gamma 1, which is here, and gamma 2, which is here, if I do the linear combination between gamma 1 and gamma 2, I get again a plan, right? Because if you imagine that I have gamma 1 which has the correct marginals and gamma 2 which has the correct marginal, I can superpose them and I get again a measure. This we cannot do it with the maps, right? Cannot superpose the graphs and I get another graph. And the marginal will be still the same, because if I do convex combination of stuff like that, here I will get always the same number. So is a convex set, and the functional is linear. So if the function here would have been strictly convex, which will be the case of this afternoon talk by Augusto, if it was strictly convex, then you have uniqueness by strict convexity, as Silvia will say. But this is just linear, so we don't get uniqueness. So the uniqueness comes from strict convexity, right? So this is just linear. We just get the existence, and we will see that actually the linearity does not really play a role. So it plays a role, but in a very subtle way. So, but I don't want to enter in the subtle. So I will say it, but it's not as clear to the day which why it's needed. Okay, so what is the proof? The proof is that it comes from the direct method of calculus or variation. So what is the direct method of calculus of variation? Is the idea is that we have something that we want to minimize. Yes. So this functional here, f of gamma, is linear with respect to gamma, right? And moreover, we are minimizing on a set which is convex, again with respect to gamma. Convex meaning that if gamma 1, gamma 2 belongs to this set here, then t plus 1 or minus t gamma 2, this belongs again to this. And again, you could use this formulation is the same. You get that if you assume this, you can easily do this. And this is linear, meaning that if I do gamma 1 plus gamma 2, this is equal to f of gamma 1 plus f of gamma 2. And this, I think, is apparent, right? Okay. So in the direct method, what we will use is basically the compactness we stated at the beginning. So we will use a topology on the space of measures, which is the space on which the functional that we want to minimize is defined. We need a topology for which use a topology such that bounded sets are compact and f is our semi-continuous. So in this case, it will be really continuous. In general, we just need lower semi-continuity. Once you have a topology with these two requirements, then it's easy to see that there exists a minimum. Why? Now, let me conclude by using these two ingredients, and then we will prove the two ingredients. And it goes always like this. You take gamma n, a minimizing sequence. What is a minimizing sequence? The minimizing sequence is just something like, okay, I have gamma n such that the limit as n goes to infinity of f of gamma n is equal to the infimum of f over gamma. So since this is an infimum, I know that there exists a sequence whose value converges to the infimum. This is just by definition of infimum. I have points which reach lower and lower stuff up to the infimum. It is not said that the infimum is actually reached, but this is always true, right? Okay. Once we get a minimizing sequence, we use the information on the topology. Bounded sets, which in this case, these are bounded because gamma n are just probability measures. Sorry. Actually, we will see that this actually is a bounded and compact sets. So this is a bounded and compact set. So in a compact set, what does it happen? That given a sequence, we have a subsequence which is converging, right? So this is compactness. So there exists gamma and k, which is converging weakly. So this is our notion of convergence that we are using here, weakly star, to some gamma bar. Okay, now, since this is compact, so we have the existence of this, and this will belong also to this. Right, this is given by the compactness. We will prove the compactness after. And now we want to say something about this gamma bar. What is the idea? This gamma bar should be the minimizer, right? But now, what is f of gamma bar? Now here we use the second condition. F is lower semi-continuous. So in this case, it's really continuous. So f of gamma bar, if it is continuous with respect to the weak star convergence, it means that f of gamma bar is equal to the limit as n goes to infinity of f of gamma n, right? This is continuity of f. So we used both of the properties of the topology, but now this is equal to the infimum over gamma of f. So we are saying really that this gamma bar is the value of the functional gamma bar is really the infimum. So this is really the minimizer, right? So gamma bar is the minimizer. And so, okay, yes, I have still 15 minutes. Yes. Yeah, because it's sufficient to have lower semi-continuous, because then lower semi-continuity, it means that when you have convergence, you just have an inequality. You have less or equal than the lim-inf by definition. But the lim-inf in this case, it's this is a converging sequence, so this is again a limit, and this is equal to the inf. So in this case, in this sense, here we are just lower semi-continuity. This is why just lower semi-continuity is needed. Okay, so in order to close the argument, now you have to prove that this set is compact, and this functional is continuous or lower semi-continuous. So we first prove the continuity, which is the easy part. Now C, we say that is continuous. Now, by definition of weak star convergence, we know that integral of C d gamma n will converge, since we have weak star convergence, this is a continuous function, continuous bounded, but then this converges to C, the gamma bar. By definition, really a weak star convergence, right? And this is precisely f of gamma bar, and this is precisely f of gamma n. So the continuity is by definition of weak star convergence. Okay, now we have to prove compactness. And for compactness, we just use Prokhorov. So, quindi, so what do we have? So we want to prove pi of mu nu compact in n plus of x, x times y. Yes, exactly. So by Prokhorov, we need what? We need that pi of mu nu is bounded. And this is okay because pi mu nu are always probability measures. And so bounded sets are just so gamma of x times y. So this is less or equal than 1. And so this is the boundlessness that we need. Pi of mu nu is closed under weak star convergence. And this can be seen as one with one of the definitions. So take gamma n, which is in pi mu nu, and gamma n converges weakly to gamma. Then we want to see what is integral of phi of x d gamma, with phi a continuous and bounded function on x, right? So fix phi continuous and bounded on x. This is in order to see what is the first marginal, right? So this is what? This is, since this is a continuous and bounded function of x, this is also a continuous and bounded function on x times y. So again, this is the limit as n goes to infinity of integral of phi of x d gamma n. But now all the gamma n have first marginal, which is mu. So this is the limit as n goes to infinity of integral of phi d mu. And this is just integral of phi d mu. So the first marginal of gamma bar is mu. And in the same way, the second marginal we have will have the second marginal will be nu. So this says that gamma bar belongs to pi mu nu, and this is the closedness, right? So I took a converging sequence here, and it converges again in the set, which is equivalent to the closeness. And now we have to prove that the tightness. Okay. For the tightness, in general, we need also another result, which is Ulam theorem, but let's say we do it in Rn. In general, it's similar, but it's a little bit more complicated. So I write what I need, and I prove it just in the case of RD in order to understand what is happening. Ulam says that if mu is a probability measure on a space X, again, a complete metric space, then for every epsilon, there exists a compact set such that mu of x minus k epsilon is less than epsilon, which is very similar to the tightness. We're actually saying that the measure mu, just the singlet, so this is mu is a tight set. Right, so if I take just the point, this is a tight set. Of course, we want to have something like that, otherwise Prokhorov doesn't make very much sense. And this, I will prove it in Rn. In general, you have to do a bit of a construction, which is a bit lengthy, and so I don't have time. So proof in Rn. So in Rn is simple, I would say. You take AR, so you take, let me say, phi r of x, which is thus the indicatrix function of the ball of radius r centered in 0, right? So this is 1 if the modulus of x is less or equal than r, 0 otherwise. Right? So now we have that mu of br of 0. Let me put it like this in order to understand that this is really a closed bounded set. So this is a compact set. Now this is what? This is the integral of phi r of x d mu on Rd. And now this, by dominated convergence or by monotone convergence, this converges to what? To the integral of 1 in d mu, which is 1. Why is that? Because these phi of r are indicatrix functions which will cover eventually all the space. So if I take phi r of x, this is converging monotonically to the function which is identically 1 on Rd. Right? So by monotone convergence, you get this limit, but this is saying precisely that mu of br of 0 will be as close as possible to 1 as r goes to infinity, right? This is as r goes to infinity. So in particular, there exists an r epsilon such that mu of br0 is greater or equal than 1 minus epsilon. And this is the same as saying that mu of x minus br0 is less or equal than epsilon. Okay, let's put it with the greater so that we have precisely the statement, right? And now this is a compact set, right? So you can do this precisely the same in every metric space, complete metric space where the balls are compact, where the closed balls are compact. If you are in a set which does not satisfy this, for example, in a Hilbert space, then you have to play with covering and balls, and it's a bit more complicated, but the idea is basically the same. You take sets which cover all the space, but you take compact sets. Okay. Now, once we have these, we can prove tightness, because the idea is very simple. We take K1 epsilon, which is a subset of X, K2 epsilon, which is a subset of Y, given by Ulam. So the ones such that mu of X minus K epsilon 1 is less than epsilon, and mu of Y minus K2 of epsilon is less than epsilon. Now we took these two sets. Now the idea is to look at K1 times K2, right? This will be K epsilon. And now we want to see that every measure which is here satisfy our tightness condition. So take gamma, which is in pi mu nu, and see what is gamma of x times y minus K1 epsilon times K2 epsilon. So we are seeing what is this, right? And this, we write it is less than this orange part plus the green part. Right? So this is less or equal than gamma of the orange part plus gamma of the green part. But now gamma of orange plus gamma of green. Why this is true? Because there are these 4 slots that are we counting twice. So we have this inequality. But now gamma of the orange, now this is a vertical set. So since gamma is a coupling between mu and nu, this is just mu of x minus k epsilon 1. And the green is just nu of y minus k epsilon 2. And so this is less than 2 epsilon. Okay, so this shows that actually this set pi of mu nu is actually tight. So we have compactness by Prokhorov. Okay, once we have compactness, we can run this business. Okay, I'm done precisely at 10, so fantastic. So I wanted to do other stuff, but it's fine like this. Okay, so if you have any questions, please comments. Not either I was super clear, or you didn't understand from first 5 minutes and completely lost you. But okay, so yes. So we use the fact that it's continuous just we used it to prove we use it just in the place where so when we say that f of gamma is equal to the limit as n goes to infinity of f of gamma k. So we just use it here, but as I said, you just need the lower semi-continuity. So in general, for example, you don't need boundedness. You just need that it's bounded from below. It can be also unbounded from above. So it can be like x minus y is allowed because it goes to infinity, but it goes to infinity. It doesn't go into minus infinity. And you can allow also for jumps in the cost. But probably I want to do at least one generalization, and probably I will do this one on tomorrow. We just need a result on approximations. Okay. Are there any other questions, comments? Okay. If you need it, so in this half an hour, I will be around, so you can ask me directly. Okay, welcome back to this second lecture in the morning, which will be by Professor Silvia Villa, which is again a professor in University of Genoa, and again an expert on machine learning, in particular optimization for machine learning, and actually she will speak about optimization for machine learning. So please, Silvia, and thank you.
Okay. So the idea is to make this introduction to optimization for machine learning, and the idea is to start from zero, let's say, and to try to arrive to the latest algorithms that are used both in the classical statistical learning setting and in the deep learning setting. And so I will concentrate on the classical framework since it's easier and it's easier to derive convergence results. So this is possible since the methods that are used are very simple, as we will see, and so do not require, let's say, many deep mathematical tools, but the derivations are usually quite elementary. Okay, so I start from the problem that is, so this is, that you should have seen yesterday. So I will try to use the notations by Ernesto for this first introduction, and then I will switch. Because in optimization, so the main difference between optimization and machine learning is that in machine learning, the variable is W, and in optimization instead is X. So I will start with W, and then I will switch to X. So the problem in machine learning usually is to minimize an objective function, which is like this. And usually you minimize on F, which belong to a hypothesis space. So, so the methods that we will see at the end will solve this problem. And more specifically, let's say machine learning, you do two things. Very often you specify more precisely what is this hypothesis space, and you assume that your function F is parameterized by some parameter. So the simplest case that you should have seen yesterday is this one, in which you consider just linear functions. And so this problem become like this, and more often in RD or W is an Hilbert space. And you minimize this expectation. And so as you can see, so the dependence on the optimization variable is if L is convex, this is a linear function in W, so this is a convex function. And this is the main, let's say, in the first variable. And then the second, maybe, so this is the first main, let's say, main characteristic of optimization problems in machine learning. And then the second one is the following. So very often you don't directly minimize that expectation, since you cannot compute it, but you have access only to a finite number of independent copies of the random variable xy. So you have seen yesterday that, and more specifically, maybe realizations of these random variables. You have just access to this training set, and you want to minimize this function instead, the regularized empirical risk. Let's already write it in terms of W of 1 over n sum. And then you add the regularization. And so this is, and I would say that this formulation is the one which stimulated a lot of research in convex optimization in the last 30 years, maybe 25, 30 years, because this optimization problem is not a, let's say, a general convex optimization problem, but it has some structure. And in particular, it is the sum of this part, which in general is assumed to be smooth. So you assume to be able to compute the derivative of this function with respect to W. And instead this one, which can be smooth, and this is the, let's say, the example that you have seen yesterday, right? So yesterday you should have seen that if you want to solve the initial problem, you can solve the regularized empirical risk where you replace the regularization, where you choose as a regularization the square norm. Okay? Yes? And then, and the other maybe, and so this is not really interesting from the new results from the optimization point of view, in the sense that this is a smooth minimization problem. So the results for this, we will see some algorithms to solve these kind of problems, but these are classical, I would say. And instead, what motivated a lot of research is the choice of sparsity-based regularizations. So the example, say the prototypical example is the L1 norm. So you want to minimize the empirical risk plus the L1 norm. And this is not smooth, okay? So it's not differentiable. And so this kind of structure give rise to the so-called splitting methods that we will see. And the other, maybe the other relevant characteristic from the optimization viewpoint is the fact that, so first you want to exploit the fact that you have the sum of a smooth function plus a non-smooth one in general. Second characteristic, you observe that here you have a finite sum. So sometimes you don't want to see this function as a whole, but you will just consider each single summand, okay? So I think I said more or less all the characteristics. So other instead, so these are maybe the mathematical, so I don't know, mathematical characteristics, features. So one, you have a structure, let's say sum structure, smooth plus no smooth. And this motivated the so-called splitting algorithms, where you split the two pieces. And the second characteristic is the fact that you have a, let's say, the empirical risk is itself a sum. And then on this, this instead motivated the development of the study of stochastic optimization methods. Okay. Everything I'm saying here, so it will be done, I will do it in the convex setting. So this is the underlying assumptions that make things, convergence theorems, let's say, as I will state them, possible. Instead, more generally, let's say from the, if we want to do instead some comments about the methods that are used, we have to keep into account other characteristics, other features of this optimization problem. So let's say the efforts of the optimization community in the last years were focused on first order methods that are very simple methods, and that they were basically discarded since, I don't know, the 70s, maybe even the 60s, because with the advent of interior point methods that are second order methods are much more effective to solve minimization problems. So why there has been a revival of these first order methods that are so basic and so simple? The motivation is the fact that first order methods, meaning methods that use only the gradient of the function f, or something similar if we don't have the gradient. So first order informations are cheap from the computational point of view. So basically what it is required is the multiplication of a matrix by a vector in applications. And this is possible even in very high dimensions. While if you use a second order method, a Newton method, you have to invert matrices. And this is much more costly. So the motivation for first order methods is the dimension of W, if you want. So, and then we have, I don't know, first order methods. And the other comment that I can make is the fact that, let's say in RD, and D is big. So I say this, and I don't know exactly what is the, let's say, the moment in which you cannot use, you have to stop using second order methods. I would say that if D is equal to 10 to the fourth, you are forced to use first order methods, okay? And the other thing which is usually big, especially in the latest applications is n. The other point is, if you want here, n, and this n can be very big, okay? So in even of order of 1 million. So in this sense, even if this is smooth, computing the gradient of a summand of 1 million terms can be long. Okay, you may prefer to have a method which computes something which is less costly. Last, let's say, last plus of first order methods. So they are cheap. Each iteration is fast. But so they have a drawback. We know that first order methods are not so effective. So they are not, it may take a long time to achieve a reasonably accurate solution. And the reason why they are still used is the fact that when you pass, so when you use optimization algorithms, so we will see that you can use to solve this problem or even directly the original one, but usually you solve this. And so you are not interested in a very accurate solution because, as you saw yesterday, when you minimize this problem, you will have other errors that come into play that are due to the fact that you are not solving the problem you want to solve, but you are solving an approximation. So you have an approximation that comes from the fact that you have just a training set, and so you will have an estimation error, okay? And you'll have an approximation that derives from the fact that you have here this regularization. So you will have a regularization error. So it does not make sense to get a very precise solution of this problem. The solution that you need is just a solution that is accurate up to the regularization error and the, let's say, the estimation error, okay? And this is the other reason why these methods are so popular. So I was saying, L is often smooth. You have seen yesterday the case of, let's say, L of, I don't know, yt equal to y minus t square. This will be our main example. And so as I was saying, this gives us the convex structure if we have this kind of dependence from the parameters W. So the main difference, maybe I want to say a word about deep learning because I think, so it's no more the time to make an optimization for machine learning lecture discarding deep learning. So I will say what, so this is a disclaimer in the sense that I don't do anything about it, but just I want to say, to tell you what are the differences and what you can borrow from what you will see in these lectures to solve a deep learning problem. So, okay. So the main difference in deep learning is the function. So I assumed here that our functions of x mapping the input into the output have this form. You can generalize this to kernel methods, let's say, to the kernel scenario. So the main difference when you use deep learning is this one, is the way in which f depends on the parameters, and the small parameter w is a concatenation of, I don't know, I think it is like this. So let me see to check that I use the same applications. Okay. And so what I assume is that these WIs are matrices belonging to DL times DL minus 1, and then the original one, so D0 should be the dimension of the vector X, which is in RD. So is equal D. So the structure of your, so and the W, let's say the small w, is just a concatenation of all these parameters. So the structure, how I build, let's say, a y. So I take my x, and then I compute w1x. So this is a vector, this is a matrix. I get another vector, which is now in D1. And then I apply, so this is an abuse of notation, I apply this phi, which is a, should be intended as applied component-wise. Phi is usually, can be smooth. So phi of t, phi, let's assume that is a function from R to R, and phi of t can be either the most famous one, which is the ReLU, so the positive part, or some smooth activation. There are many. Just, I don't know, for instance, the arctange. Okay, or other smooth activation. So what is important here, and you apply this to every component of your vector. Once you do it, you do another linear step, and you transform this in another vector. So as you can see here, you immediately lose convexity with respect to W. This is not linear in W. And so this destroys the convexity of your problem. What has been mainly used in this context is stochastic gradient descent. So the algorithm that is a stochastic method. We will see. So the algorithm that we see in the convex setting applies to the non-convex setting, and indeed is the most applied in the non-convex setting. You may find variations. Maybe you have heard about Adam. I hope to briefly mention it, but this is a variation of a stochastic gradient descent. So the point is that in this setting, all the properties that we will see in the convex setting in general do not hold. So the convex world is the ideal one, is much easier. And the other point that, so there are other subtleties from the mathematical point of view. So optimizers, let's say the optimization community has started to be interested into this problem. And maybe in the smooth setting, you just have the problem of non-convexity, while in the non-smooth setting, you have the problem of defining, let's say, a proper subdifferential, so a proper surrogate of the derivative. And on top of this, you have the problem of computing the derivative of a composition. So this is usually computed by backpropagation. But from the mathematical point of view, applying backpropagation, which is based on the chain rule, requires the chain rule to hold. And this is one of the points where the optimization community focused most in the last year. So stochastic gradient descent. And the other one, we'll see that this is not very correct. And the other one is, let's say, chain rule. So I will not talk about this. But I think these are two, so especially this one is a very interesting direction. So working on this, there is let's say, the Toulouse group. Bolte, Powells are the two names of optimizers that try to understand why stochastic gradient descent works in this setting. Okay. Okay, so. So, oops. So after this introduction now, so I organized the presentation in this way. So in this lecture of today, I will start from the smooth setting. And in this setting, so as a problem that can be solved with this approach, we have to think to the empirical risk regularized with the square norm. And so the algorithm of choice is the gradient descent. Then this afternoon, I think we will see the case of the non-smooth setting. And I guess this afternoon I will be able only to give you the tools that are needed in order to analyze this case. And in the third lesson, I should be able to present you so the non-smooth structured with the algorithm, which is proximal gradient. And lastly, So in the last instead talk, I'd like to discuss some extensions, let's say, and variations. So for sure, we will see stochastic gradient descent. And the other things that I'd like to present you are accelerated accelerations and maybe adaptive algorithms. So this is the family that I was speaking about. Adam belongs to this. So the ADA family, let's say, ADA grad, I don't know, ADA delta, there are many, NADAM, I try to, there are so many. So this is the plan. Okay. I will start with some preliminaries on convex functions, and in particular today, I will focus on the convergence in the strongly convex setting. So there is a huge difference in the convergence results that you can get in the convex setting and in the strongly convex setting. So I will start, let's say, gently with smooth convex functions, which are strongly convex. This is the best scenario that you can hope for first order methods. And then I will go towards the just convex case. So maybe before doing this, I forgot, it's good to say, so all the theorems that we will see are of the same, have the same structure. And basically what you want to prove is some convergence rate on the algorithm that you are using. And so just maybe it's good to recall what is the performance of an algorithm. So I will use the framework that has been introduced by Nemirovsky and Yudin, and then developed by, for instance, Nesterov. So the idea is that of what is called the model-based optimization. What you assume is that to build your algorithm, you have access at each step to an oracle. And this oracle, depending on the properties of the oracle, you can classify the algorithm. So we will see algorithms that have access to what are called first order oracles. So what does an oracle? You give him a point and it tells you, for instance, the value of f at the point you gave him, the gradient of f of x, and we will see the analogous of the gradient in the other cases. And then you measure the performance of the algorithm in terms of the number of calls to this oracle. So the let's say the performance is equal to basically what you in order to find an epsilon solution. That means so now I turn my, so maybe the problem now is this one. In order to find an epsilon, I will always, so there are many results in which you don't assume that f has a minimizer. I would say you don't lose much if you assume that the function has a solution, okay? So I will always restrict, so if I forget in some results, this is an error in the sense that I will always assume that a minimizer exists. So, and you look for epsilon accurate solutions, meaning a function which is in this, for which the value of the function is less than the minimum plus epsilon, or the other case is this one. Let's say maybe write it correctly. Oh, no. I don't know. Let's write it like this because otherwise. if the minimizer is unique. So this is less precise. I mean, so usually this is the notion of convergence, which is used in machine learning, and is the one in order to assess the performance of an algorithm. Sometimes you are very lucky, as we will be in this first lecture, and you can, you have to assume that the minimizer is unique, and you can hope to get for an estimate also for this quantity, this difference in norm. So keep in mind that we will do the analysis in H. Hilbert space. So in general, having even convergence in norm is impossible. Okay, so the cases in which we will be able to estimate this quantity are very limited. So this is, and I would say also this is the main difference between the optimization community as it was before machine learning and the machine learning community. Now machine learning community and optimizers are really overlapped in the sense that they have really common interests. A lot of machine learning problems triggered, I think, really the research in optimization and vice versa. And this has been a switch in the sense that the main interest here is convergence of the function values rather than convergence of the iterates. We will see, so I will try to give you both the analysis of both quantities. So when we want to estimate the number of calls to the oracle, very often we approximate this quantity by the number of iterations, in the sense that at each iteration, usually you call the oracle once, sometimes twice, and so it's a very good estimate. So at the end, you just have to multiply by a constant. And so this is the classical convergence analysis. So the performance is evaluated in terms of number of iterations. Okay. So now I can start by introducing the first algorithm, that is the gradient descent. So I guess maybe all of you know the algorithm. So the algorithm looks like that. And so the analysis, as you can see, so you start from a point, an arbitrary point, and then you construct, you build your sequence recursively by subtracting at the point xk a descent direction, which is the one of the gradient. So of course, I assume that the gradient exists. And you multiply this gradient by a step size. So this is called step size. So as you can see in this algorithm, there is just one free parameter, which is the step. And so the results basically that we will see state convergence of this method under suitable choices of the step size. There are many choices that are possible. So I don't know, something like decreasing to 0 in a monotonically way, monotonically. The other one is constant. And then there are, I don't know, adaptive choices, in the sense that you can choose the step depending on the point where you are. So for instance, this is called also line search. So these are basically the variations on this. These are basically the possibilities. So you have convergence results for each of these choices. Either the step size goes to 0, or it's constant, or it's in a sense chosen in a more clever way, in the sense that here you look at the direction given by the gradient minus the gradient, and then you look for the best step size, the one that gives you the biggest descent. And you choose this gamma in this way. Since we will deal always with the convex setting, we will focus on the simplest case, which is this one. So step size fixed. This one is never used, I have to say. We'll see it's used mostly in the non-smooth case. This is every time that for an algorithm you have to choose a sequence which goes to 0, this is not a good sign. In the sense that when you practically have to implement the algorithm, it's not clear what you should do, right? If you have something like this, on your computer will do a finite number of iterations. Probably instead of a 1 here, you can put a C. And basically, you have no recipe to choose your step size, okay? Because you will do, I don't know, 100 iterations. If you start with C equal to 100, 1000, makes the difference. And this is really a shortcome of these kind of step choices. These are used to ensure convergence, because you can do the analysis, but these are not very good in practice. This constant step is the best choice. You have to choose one parameter, and then you're happy. And this is also the reason of the success of these methods. They are very simple to implement. Okay. So just a basic counterexample to show you that this step should be chosen. And the example, maybe, I think you have seen it already, is so we are in R, and we take a parabola. And then what happens is that if you do the gradient descent, the derivative is just x. And so if you start from x0, I don't know, different from 0, because otherwise it's finished. So you define, you will have something like this. And so this is, okay. And so what happens is that if gamma is less than 1, then this quantity, or even less than 2, this quantity goes to 0, right? If gamma is bigger than 2, what happens is the following case, the following situation, in which you go on the other side, but you go more than a reflection. So you have something like this. And so the algorithm does not converge. So here you have this quantity which is bigger than 1. And so basically the convergence results state that if you choose gamma small enough, then you have convergence. And basically, the game here is to choose it small enough, but sufficiently big, in the sense that you still have convergences if gamma is very small, but here you have basically 1 to the k that goes to 0 very, very slowly. I don't know, if you take gamma very small, you will have very slow convergence. So in order to state convergence, I need to give you some, I need to state some preliminaries. So the convergence of the function values of all these methods is based on inequalities. So I will write a series of inequalities. I will not prove them. And I will concentrate on the proof of convergence results. Otherwise, I spend all the time on these preliminary results. Okay. And basically what we need are some relationship between, let's say, the characterization of convexity in the differentiable case. And then, as I was saying, I will focus on strongly convex functions. So you have, this is a proposition, I don't know. So you have a function which is differentiable. Then the following are, so since H is a Hilbert space, I always assume Frechet differentiability of the functions, okay? And if you are not familiar with infinite dimensional space, everything is almost the same in the finite dimensional space case. So usually, indeed, I do these lectures in the finite dimensional case. So I just needed to check some additional points, but are really very few points where you have the difference. Okay, then the following are equivalent. So 1, F is convex. 2, for every y, for every x, you have something like this. F of y is bigger than f of x plus the gradient. So what we are saying is that if we have a convex function, so a characterization indeed of convexity is the following. I take the point x, at every point x that I take, I can draw the tangent line, let's say, or the tangent plane, whatever. And hyperplane, what happens is that this line is always below the graph of f. This is a characterization of convexity in the smooth setting, okay? So this should happen at every point. So we'll talk always about globally convex functions. These are convex on the space. So, and the other, so you can write something similar, which is the following. So an equivalent formulation of convexity is this one, in the sense that you can ask, so the f being convex is equivalent to some kind of monotonicity of the gradient. You see here, if we would be, let's say, one-dimensional, then this would imply that the first derivative is increasing, okay? And so this is called the monotonicity of the gradient. And then in the case, so I just write it because it's maybe one of the most practical ways in which you prove convexity. And convexity is often proved by showing that the second derivative is positive semi-definite. So, and this, of course, if f is twice differentiable, then all this stuff is equivalent to 1, 3 are equivalent to asking is positive for every v in H. With this, I mean the second derivative. Okay. So this is these are the characterization of convexity. Now, these are used in order to derive, let's say, more powerful, maybe, estimates in the strongly convex case. So I write just the definition of strong convexity because I don't know if it's familiar to everybody. So f is said to be, f is strongly convex. So all my functions will be from H to R. So if I have the following inequality. Why? So my function is strongly convex. Let me be of modulus mu. Okay. And this should be true for some mu bigger than 0. So what happens is that not only I have the convexity inequality, meaning that if I compute f at this point, the value of the function here is under this segment, but I ask also for a gap, which can be measured in terms of this quadratic so the distance between x and y, and this let's say this is just to take into account that the things are going smaller when you go towards x or y, and you have this mu, which gives you the curvature of this quadratic function. Okay, so this is strong convexity, and strongly convex. You have to keep in mind that strongly convex functions are the heaven for optimizers, in the sense that are the best behaved functions, and in particular, you can improve these inequalities. Maybe just in the interest of time, since I'm going too slow, I just use this. Sorry about this. So I need, so this is really strongly convex, mu, and this is differentiability and strong convexity. Okay, then F is strongly convex. Here, what I have, f of y is not only bigger than the tangent, but I can add a quadratic term. Okay. Yeah. Yes, so it's yes, gives you a kind of quadratic behavior. And the other thing that gives you, so this may happen, but the function may not be strongly convex. The point is that the curvature of this parabola is constant. So you have this. So you can see it very clearly from this inequality, I guess, right? Because at each point you have that the graph of your function is bigger than a quadratic function, okay, which is tangent at x, and whose curvature is given by this mu. No, I think is positive definiteness for the second derivative.
Okay.
So it's from below.
Okay.
And instead we will see that what you're saying is related to the Lipschitz smoothness of the gradient. Okay. Lipschitz continuity of the gradient. Okay.
It's one-sided.
So here you can replace this inequality that was, I had 0 in the convex case. I can put mu x minus y square. And again, if this is called strong monotonicity of the gradient, and if f is twice differentiable, then all these things are equivalent to the fact that this is positive definite. So the second derivative has the smallest eigenvalue, which is mu. Mu, sorry, yes, thanks. Yes. Okay. Yeah.
Is this equivalent to require that the inequality is strict if x is different from y? Or
So this implies this. So what you are saying is if you modify the definition of convexity and you do this, this is called strict convexity. Is the notion that Simone was mentioning this morning, and this is weaker than strong convexity. So you have strictly convex functions which are not strongly convex. Now I don't have so I don't know what, maybe minus the logarithm should be strictly convex but not strongly convex.
To the power 4.
Yeah, or yes, exactly.
okay.
X to power, yes, as well. Yes. Okay, so you have strictly convex functions which are not strongly convex. But of course, strong convexity implies strict convexity. If you want, is a quantitative version of strong convexity, strict convexity. Okay, and then lost. The last part is about, maybe I should say something because I will use them between the let's say the relations about the relations between strong convexity and minimizers, in the sense that you can prove, so I will not prove this, but so F is strongly convex, then it has a unique minimizer. Exactly one. So you can prove existence always, and this minimizer is unique. And moreover, if this is strongly convex with parameter mu, then you can prove the following inequality. So indeed, to be honest, you don't even need differentiability. Okay, so it's true also if f is non-differentiable. And then instead, if f is differentiable, and this is easy because you just put a minimizer in that inequality in number 2. If you choose
so X to be a minimizer, you get exactly this inequality. And instead, the second one is less obvious. Still easy to prove. So as you can see, you can state let's say the difference between f of x and its minimum is upper bounded by the square norm of the gradient. So this inequality is called the Loyazievich inequality. And this is this is interesting in the sense that tells us that strongly convex functions satisfy the Loyazievich inequality globally. So this is true for every x in H. And while this inequality, and we will see that using this inequality, just this inequality, you can prove linear convergence of the gradient. And this is relevant in the sense that this inequality can hold even in the non-convex setting. And indeed, the analysis of first-order methods in the non-convex setting have been made mainly assuming a condition like this. Okay, so this is an inequality which is quite useful in recent years to study convergence. Maybe the names maybe are again Bolte, and another name is Attouche. These are people that more generally yes, sorry. So I start to be more relaxed. So okay. So in the strongly convex setting, you can, let's say, you can control the convergence of the function values in terms of the gradient. And the other thing, you can control the convergence of a sequence to the minimizer in terms of the function values. And this is these are quantitative controls, let's say. Okay. So an example before going further, since I said that this Loyazievich inequality can be satisfied, so it's satisfied for sure by strongly convex function, but is a less demanding notion. So the classical example in which this is used is the following. Here you have to require that for the easiest case is where you are finite dimensional. So A is a linear function. So in general, so this function is strongly convex if and only if the smallest eigenvalue of A star A, so if so the matrix A star A is invertible, so of A star A is positive, then the function is strongly convex. Then F is strongly convex. And the modulus is really the one of these smallest eigenvalue. If instead the smallest eigenvalue is 0, the function is not strongly convex anymore. You will not have a unique minimizer, but still it satisfies the Loyazievich inequality. And the constant is given by the smallest non-zero eigenvalue. So okay. And this is the typical setting. Again, in machine learning, usually you don't have invertibility of these metrics. Okay. So the last chapter of preliminaries is about the relations, the characterizations of the Lipschitz continuity of the gradient, which is the other ingredient which is needed in order to prove convergence of the gradient method. So let's say Lipschitz continuity of the gradient and convexity. So in the convex setting, you have this characterization. So theorem or proposition. So I need F, which is differentiable. Then the following are equivalent. So first, the gradient of F is L Lipschitz continuous. So for every x and y in H, the gradient of f of x minus the gradient of f of y is less or equal than L times x minus y for some L bigger than 0 or equal to 0. Maybe let's put bigger. And then I divide. And then, so this Lipschitz continuity of the gradient is equivalent to what is called the descent property. So this is true only in the convex setting, this the equivalence. So for every x and y, you have the following property. F of y is less or equal than f of x plus the gradient plus L divided by 2 x minus y squared. So to come back to your to the question of somebody, the point is that strong convexity give us a control from below, so the function should be sufficiently curved, while the Lipschitz continuity of the gradient give us a control of the function from above. So at each point, I should be able to put a quadratic function which is good for everybody. So it should be tangent, maybe more or less here. And this should be with the same curvature everywhere. So this is usually called the one implies two. It's called descent lemma. And this is the key. So when you do prove convergence of a first order method, you start usually from here. And the third property instead is the following. So you have the following property, 1 over L okay, so okay, so it's easy to see, so it's immediate to see that this implies Lipschitz continuity of the gradient, but it's not obvious to pass from one to this inequality. This is called, this is a theorem. It's called Bayon-Haddad. So it's still an elementary proof, and it states basically that the gradient is co-coercive. So this property is called co-coercivity. In general, for operators from H to H, Lipschitz continuity is weaker than co-coercivity. So this is clear from this inequality. You always get Lipschitz continuity if you have a mapping that satisfies this inequality. And the reverse is not true. So it's true only for gradients. So this is a property of the gradient. This is not true for other monotone operators. Okay. And and again, so maybe I should write it. If f is twice differentiable, you can you get the characterizations in terms of the second derivative, and this time the second derivative should be bounded from above. So you have that should be less than L v squared. It's not written well, but okay, again, since it's here, this is the classic example of a function which has a Lipschitz continuous gradient. the Lipschitz constant of the gradient, this time is the biggest eigenvalue of A star A, okay? So this is a Lipschitz continuous gradient. Very often in the papers, you find this property of having a Lipschitz continuous gradient is called L smoothness. So when you see L smooth, means that the gradient is Lipschitz, L Lipschitz, okay. So, and this is exactly, sorry for the notation, this is exactly the setting of, that you have seen yesterday, of regularized least squares, where if you use the quadratic loss, the empirical risk will look exactly like this, right? So maybe I change just to give you something that reminds you, I think, maybe the notation of Ernesto is this one. So they regularize the empirical risk when maybe you don't need this. So the regularized empirical risk is exactly this, okay? So you have a quadratic function, which is strongly, maybe not strongly convex, but satisfies the Loyazievich condition, and is as a Lipschitz continuous gradient. Okay, so finally, the last theorem, which is in a nutshell the proof of the convergence of the gradient descent. Basically, you can so it's super late. You can put together these two, so the strong convexity and the Lipschitz continuity of the gradient, and you get an inequality which puts everything together. While these inequalities, you can find them in every book of convex optimization. This one of strong convexity, you can find it is more difficult to find. You can find it, for example, in the book by Nesterov, Introduction. I don't remember how it's called. The book is like a basic course on optimization, something like this. And so in this case, you take F, which is differentiable and strongly convex. So let me write L smooth so that it's faster, and mu strongly convex. So what you get is that then you have the following inequality, which holds. That is the following. So then, okay. So I wrote it. I'll tell you later. So you can mix basically the inequalities that we have seen below, and lower bound this product in terms of the distance of x to y and gradient of f of x minus gradient of f of y. And indeed, I wrote it not in the good way, in the sense these two, if f is differentiable, the fact of satisfying this inequality for every x and y and being L smooth and mu strongly convex are equivalent. Okay, so this is a characterization of strongly convex functions with Lipschitz continuous gradient. And so this will be the key to prove that the gradient method converge. So we see it this afternoon, I would say. Yes. So that we finished. It's true. Now I have to start. Oh, no, I have half an hour. Okay, fantastic. Sorry. So I was thinking that it was over, so I was pretty sad. But now, so it's fine. Perfect. Okay. No. I'd like to finish. So, but yes. Okay. Yes, it's true. There is time. So maybe it's a good time for questions. Sorry. If you have doubts on this finishes, let's say, the static part. Now we go into the dynamic one.
But convexity implies almost algebra differentiability? Or...
This is true, yes. But I will never use this.
Oh, you never use, okay,
no,
okay, okay.
No.
Right, okay.
So we will see, I will use, so when the function is convex but not differentiable, I will use the subdifferential. Right? So I will not need to use the gradient. So there are, indeed, recently, I came into a paper that is called, the methods that are still first order methods. These are called gradient sampling methods. So the idea is really to to exploit the fact that functions that are used in machine learning are usually non-smooth in very small regions. For instance, L1 is just non-smooth on the edges, let's say, on the axis. And then you can try to estimate, let's say, to move according to an average of gradients in order to around the point that you choose, and you will be lucky in the sense that you will get points of differentiability. This is it's used in this. It's the only algorithm in which I saw this property used. Otherwise, you use differentiability. Sorry, the subdifferential. Okay. Theorem. So, and this is the convergence of gradient descent. So I do it in a very special case, which is the one in which f goes from h to r. And okay, this is differentiable, and this is needed because I do a gradient method. And then the other thing which is very useful is gradient of f is Lipschitz continuous, L. And the other one is the fact that f is strongly convex. Okay, then, and sorry, then I have to define the gradient. Let me define again the gradient sequence. So let x0 in h should be, it's a in x0. And then xk plus 1 is equal to xk minus gamma, the gradient of f at xk, with gamma less than 2 over mu over L, mu plus L. So this is the positive. So this is the upper bound that I was telling you before. So you need, in order to establish convergence, you need to choose gamma small enough. And in this, for this convergence theorem, the small enough means twice divided by the Lipschitz constant plus the strong convexity constant. Then what you can prove is the following. So maybe right before. And f of xk. So, sorry. Divided by 2. Okay, so just some comments. So here I didn't define it, but this is the unique minimizer of f. F is strongly convex. So we have at star is the minimizer. Okay, and as we can see, we can derive this kind of convergence. So this is okay. This quantity xk minus x square decreases exponentially. In optimization, this is called linear convergence. So I forgot to check why. Every time I check why it's called linear convergence, I don't remember. So, and the same kind of convergence you can find for the let's say sequence of the iterates and the sequence of function values. Just some additional comment here. So as you can see, the speed of this convergence will be determined by the let's say how small is this quantity in this parenthesis. So it's our interest to choose gamma in order to minimize this quantity. So taking into account, this is just a minimization of an upper bound. So we minimize the upper bound, we will have an optimal choice for the step size. So, but we still minimize an upper bound. So we are not sure that in practice, this is the best possible choice, okay? But minimizing the upper bound, what we get is that gamma should be chosen as equal to 1 divided mu plus no, sorry, 2 divided mu plus L. 2 divided mu plus L. And indeed, because I was wrong, sorry. This is a special convergence theorem and is unusual. So in all the results, you have always gamma that is strictly less than the upper bound. And here instead, in this special convergence, you can arrive to the upper bound, and the upper bound is the optimal choice. So and if I did well the computations, what happens is that in this case, so it should become like this. So you have this, and the same for the function values. This is xk, this is k, and this should be 2k because what you maybe 2k, yes, because you get this squared when you replace mu. Okay, and as you can see, so what determine your convergence, here you can write it in a slightly different way. So I can divide by, for instance, L minus 1, mu over L plus 1. And so, as you can see, the magnitude of this number is determined by this ratio, so mu over L. So if mu over L is big, then this quantity should be small. No, sorry, mu over L. So I want a big mu and a small L. So sorry, maybe one thing that I never said is this fact, in the sense that mu is always smaller than L. Okay, you have a quadratic lower bound and a quadratic upper bound. So, and the best you can hope here is to go to mu over L close to 1, so that this quantity becomes very small. Okay, and you have a faster convergence. Instead, things do not go well when mu over L goes to 0, and in this case, this quantity will be close to 1, and then you will have a very slow convergence that in the first iteration may be even slower than the one that we will see for the convex setting. Okay. Okay. So what happens? Maybe we can prove this theorem. And basically what you do is that you define this operator, identity minus gamma the gradient. Okay, this operator depends on gamma. And what you can prove is that this operator is a contraction for every gamma that is that satisfies the assumption. Does everybody know what a contraction is? Yes. Okay. And so if you iterate a contraction, we will get automatically this kind of convergence. Okay. This will be the Lipschitz constant. Okay. So basically, we should start from the inequality that I wrote before, putting together strong convexity and Lipschitz continuity. So this one. So we know that okay, and then so this should be correct. Okay. And then basically what I will have is that I will have gamma the gradient. So I will get something which is multiplied by 2 gamma. So I have this inequality, which is true for any x and y. And now I just write, so I want to prove that this T gamma is a contraction. So I just need to write T gamma of x minus T gamma of y. I do it square. So this is x minus y square plus gamma square And then I have the okay. I just developed the square. And now I know that this quantity is bigger than this, so I can majorize because I have a minus in front of it. So this comes, so I can replace this with this. And so what I get is 1 minus 2 gamma mu L divided mu plus L x minus y square. And then I get plus gamma, which multiply gamma minus 2 over mu plus L okay. And then what I see is that since gamma is bigger or equal than 2 over, since gamma is smaller or equal than 2 over mu plus L, this quantity is negative. So this is negative, and therefore here I have that this quantity is less or equal than this. Okay, and this is smaller than 1, you can check. Sorry, it's positive, of course, and smaller than 1 because this is positive. Okay, so this immediately implies the first inequality, this one, iterating, and then instead the second one is again derived by the Lipschitz continuity of the gradient, is an inequality that I didn't write before, but is derives immediately from the Lipschitz continuity of the gradient. And then by the descent lemma, you can write that f of x minus the minimum of f is smaller than L divided by 2 x minus x star square. Okay. And maybe another thing that I didn't say, is it clear? Because I forgot to say one important thing, that is the fact that, so we know that when you have a contraction, the fixed point iterations converge to a fixed point of the contraction, and of course, the fixed points of these contractions are is the minimizer of f, okay? So maybe one thing I forgot is x star. Okay, maybe the comments that I wrote that I should say are, so many of them I already did. Maybe one thing that I should say is that in this theorem, so this is a very good convergence rates for first order methods, but in this theorem, what you need to do in order to get the best convergence I showed you is to choose gamma equal to this quantity. So let's keep in mind the examples of quadratic functions, which is the easiest one. So in that case, we know exactly what mu and L are. So if we consider f of x equal to this, then the mu is the smallest eigenvalue of A star A in the strongly convex setting, and L is the biggest eigenvalue of A star A. So from a practical point of view, it's quite easy to compute the biggest eigenvalue. So you just need to compute you can use an algorithm which is quite efficient to compute the biggest. But in order to get mu, you need to get all the eigenvalues. So you need to diagonalize A star A. And so this is much more costly. And so usually having a good estimate, usually you estimate this mu, having a good estimate of mu is difficult. And choosing the wrong gamma really makes let's say the convergence worst, okay? So this is if you want, a tricky part of this theorem. The choice in practice of a good step size is difficult, okay? So it's very easy to underestimate mu. And the other thing which is instead very good, and again, I should have stressed it even more, is the fact that in this strongly convex setting, even if we are in an infinite dimensional setting, we are able to get convergence in norm of the iterates. And this is the only case where it happens, okay? And even more than this, we are able to get a convergence rate which is quantitative. So we are able to estimate the speed of convergence. Now, so what I will do in these last minutes is to extend, so to do, let's say, an analogous theorem, but using only the fact that F satisfies the KL inequality, the Loyazievich inequality, okay? And we can see what you can do in that case. We can also assume that F is strongly convex in the sense that what will happen with this new analysis is that we can choose the step size, let's say, above the threshold 2 over mu plus L. And so this is the first improvement. The other thing that is good to note before stating the theorem is the following. So in this theorem, what I used is that the idea behind the proof is the fact that I see the algorithm as a fixed point iteration. And this we will see this afternoon will be the good point of view in order to assess convergence of the iterates. But then instead, if you want to speak of convergence of the function values, very often you forget about this interpretation of the algorithm and you use another interpretation. And more precisely, the interpretation of the gradient method is the following. You have a function f, you want to minimize this, and what you do is the following. You take, this is related to the descent lemma. We know that we have an upper bound, quadratic upper bound here, which is like this, and this is f of x, so f of x, of x plus the gradient of f of x, y minus x plus L divided by 2, y minus x. So a whole class of methods that are called methods that are maximization, minimization algorithm, minimization, are constructed exactly like this. So you start from your function f. You are at a current point x. You build an easy upper bound. In this case, this is this quadratic upper bound. And then what you do? You minimize it. You minimize the upper bound and you get a new point, let's say x plus. Okay? And since you are minimizing this, and let's call this g of x, g of y, let's say x. And then what happens is that at the point x, the upper bound coincides with f. So when you minimize the upper bound with respect to the first variable, you will get a smaller value. So the algorithm will be descending. And this is a good news. We always like algorithms that are descending because each step is a gaining. Okay, is a gain. And so the idea is to, so you have this. And the hope, and that's exactly what you do and what we will do in the proof, is to prove that this descent is sufficient. So this is not enough in order to guarantee convergence to the minimum. You can stop before. But instead, if you guarantee a sufficient decrease, so here we will be able to put something negative, then you can prove convergence of the algorithm. And this is I would say, the idea of the proof behind all these inequalities that you will see is this one, and is used even more generally than for gradient descent. Okay. So the theorem is the following. So for the first part, so it's differentiable. And satisfies the Loyazievich inequality. Then, so maybe so what I have to say, let gamma be less than 2 over L, and bigger than 0. Then, so what I can prove is the following, and I assume that the minimizer exists. Oh, sorry, that's what. The following. Okay, I will prove only this one. Indeed, if the function is convex and it satisfies the Loyazievich inequality, it can be shown that it satisfies it's called the quadratic growth condition. So the inequality that we saw between the function values and so you have something like this. From the let me call the set of minimizers the argmin of f square, and here I don't remember where you put the constant according to my notation. I think so. It should be like this, hopefully. So in general, if f satisfies the Loyazievich, then you can, and is convex, then you can prove this. And then you cannot prove any more strong convergence to let's say with this proof. You cannot prove convergence to a minimizer, strong convergence to a minimizer, but you can still upper bound this quantity, okay, in terms of the function values. So we will not see this. Okay, I just write the proof for this because it's easy. So it starts with, as I was saying, this point of view. So by the descent lemma, what you get is that f of xk plus 1 is less than f of xk plus the gradient of f at xk times xk plus 1 minus xk plus L divided by 2 xk plus 1 minus xk square. Then what I use is just the definition of xk plus 1. So this is f of xk plus the gradient of f at xk. Here I have a minus gamma. So let me write it already like this. Okay. Plus, here I have gamma square divided by 2, gradient of f xk plus xk. Okay. So I just use the fact that xk plus 1 minus xk is minus gamma the gradient, and then here I can, I don't know, rewrite this slightly better. So I get plus, minus, maybe I want to write, minus gamma, which multiplies 1 minus L gamma divided by 2. Okay? And now I use the fact that I have that inequality, so f of xk minus the minimum of f is smaller than 1 over 2 mu, the gradient of f. So the gradient of f at xk is bigger than 2 mu f of xk minus the minimum. So here first I have to add the minimum on both sides. And now here I can put 2 gamma mu. And this is true since this is positive. Okay. Okay, what I did, so I need to assume this is positive, this is true. Okay, given the choice of gamma. And so this is finished, right? Because I find that recursively f of xk plus 1 minus the minimum of f is less or equal than 1 minus 2 gamma mu, 1 minus L gamma divided by 2, which is exactly the constant that is written above. And okay, so that's it. And so, as I was saying, this is an interesting point of view for 2 reasons. One is that you can choose the step size up to 2 over L. You pay, let's say, if you do the computations, you pay the price of asking a less demanding assumption on the function f, because the quantity there, so I should write the optimal gamma, which I don't remember, of course. So 1 over L, yes. And so what I should get, okay, so let me see. Okay, so I will not be able to do the computation. So what is this? So this is 1 over L, so this is 1. And then I get 1, this is 1 minus mu over L. So this is L minus mu divided L. And so I'm not sure I wrote it correctly. In the first, maybe I did everything in the wrong direction. So in the first, sorry, I think in the contraction theorem before I wrote mu minus L, but it's L minus mu. So L is always bigger than mu, okay? Sorry about it, so check please. And so what you get is that this quantity is always bigger than this one. So it's bad, it's a worst as a convergence rate, okay? And that's what you pay by, let's say, not using strong convexity. So you use a weaker inequality. Okay, so that's it. On the other hand, let's say this is interesting in the sense that this kind of derivation can be generalized to the non-smooth setting as well. So you have similar results in the non-smooth setting and under similar assumptions. Okay, so see you in the afternoon. If there are questions, sorry.
Yeah, no. Thank you very much. So you have questions, comments? Okay, I have a question. So this last one, you don't require convexity?
No, yes, you do. So everything that I write is assuming convexity of F. Oh, you can do, I think, maybe you can write, so indeed I never use it, probably I never used it. Because the descent lemma is true, even in the convex. So if you assume Lipschitz continuity of the gradient, it's still true. Then you write this, and this is still true.
Yeah, and Loyazievich is just
yeah, you can
relating to the minimum.
Require it. So there are non-convex functions which satisfy Loyazievich. Yes, probably it's also. Yeah, indeed. Okay. So to be more precise, so the analysis under the Loyazievich condition usually is done in the non-convex setting. The difference with respect to what we did here is that you don't ask it. You don't ask the inequality to hold globally, but you ask it only on usually on a neighborhood of the solution on a suitable sublevel set, because otherwise it's very demanding. So there is a paper by Nuttini and Schmidt which analyzes this property in the non-convex setting. And so there are examples, but still, if you ask this, as you can see, you have every critical point should be a minimizer, right? A global minimizer. So you can do it in the non-convex setting, but the situation, so it's a very special class of functions. Yes, it's correct.
If you have convexity, you get convergence in for the distance between x and argmin, right? So
yes, this is true.
Yeah.
So
Again, so there are three concepts that are related, that are this Loyazievich inequality, metric regularity, subregularity of the gradient, and the growth condition that I wrote. So in the convex scenario, they are all equivalent. What I guess is that in the non-convex, you can still prove that, I think that is still true that Loyazievich implies quadratic convergence. What is not true is the opposite. So you can still prove this, I think, even in the non-convex setting. So it should be checked, but I think it's true.
Okay, so thank you very much. Thank you, Professor Villa. Okay, so welcome back to this afternoon session of 2 lectures. And I'm glad to present you Augusto Gerolin, next speaker, and also one of the other organizers of this school and then workshop. So he's a professor in the Department of Mathematics and Chemistry, and in particular is a Canada Research Chair in AI, Math and Chemistry. So he do everything. And he's at the University of Ottawa. And he will continue speaking about optimal transport, in particular with entropic regularized optimal transport. Please, and thank you.
Thank you very much for the wonderful introduction, Simone. So it's true. So like I'm follow up the first lecture done by Simone this morning. So the first talk of this morning. So I really count on you guys. I have a very strong jet lag because I just arrived this morning and we are after lunch. So like you should ask as much questions as you can. So like this, we both keep awake. So I would probably sleep if I was not speaking. There is also a risk that I sleep while speaking. So like just to warm up before introducing like the entropic regularization of optimal transport. So just to recall a little bit something that you saw this morning. So what is the Monge-Kantorovich formulation of optimal transport? So our data, we have like 2 measures, mu and nu, let's say measures in RD, for example, with finite second moment. So if you want to fix idea, so think, for example, that mu are like these 2 bumps in like dark green, and nu are like the same 2 bumps in light green on the right picture. And like in the Monge-Kantorovich formulation of optimal transport, what we are looking is for the best coupling. This means the best probability in the product space having the marginals equals to mu and nu. So like to the best coupling between mu and nu. So like in this picture, you see an example of a coupling gamma. So this is not the optimal transport, the optimal coupling for the distance square cost. And like, of course, optimal, as you see this morning, is in the sense that like minimize the cost, so the integral of the cost function that you are fixing x minus y squared integrated to the gamma. So like after the talk today, like you should not be afraid to write directly mean for this variational problem. So we have seen that like this set pi of mu and nu of couplings between the probabilities mu and nu are compact for the weak star topology. This is also a convex set. And this functional is lower semi-continuous to the same topology. So we should not be afraid to say that like the minimizer exists. So what can we do with this? So let's take an application, an example. So imagine that like mu is a histograms of colors of a painting of Picasso, and nu is a histograms of colors of La Gioconda. So in which sense, like we are constructing this histogram. So like, what is an image? So an image for a computer is like a set of pixels. So in each one of the pixels, we have a vector in R3. So that this vector in R3 are telling you like the tones of red, green, and blue, the RGB. So like what you do, so in every pixel, you extract these colors of red, green, and blue, and you basically make a histogram of those colors. So here you see a histograms of Picasso, and here you have a histogram of La Gioconda. And since those are probability measures, we can like use the optimal transport map and send the colors of Picasso to La Gioconda and vice versa. So the optimal transport map between mu to nu send the histograms of colors of Picasso to the one to La Gioconda, and the optimal transport map between mu and nu do the opposite way. So in this like is basically using metric properties of this functional. So here there is no feature extracting, there is no machine learning or deep learning. This like is basically thanks to the structure of this this functional, because actually this functional defines a distance in the space of probability measures. And this distance, like, of course, with a lot of technicalities that we would need to go on, like metrizes the weak star topology. So this is the metric of the weak star topology that we introduced this morning. So saying that, like, why this kind of metric, just to give a feeling, a very intuitive one. So why this kind of metric is very reasonable, or why this kind of metric makes a lot of sense to compare this type of data, for example, colors of histograms. So just to compare, think a little bit about like a LP distance, and now we compare with a Wasserstein distance. So imagine that your distributions mu and nu, they are like absolutely continuous. So they have densities F and G. So mu has density F, and nu has density G. So if you compute the L2 distance, or the LP distance between those densities F and G, you are basically computing a vertical distance between those densities. While the optimal transport, the W2, so the Wasserstein 2 distance, or the optimal transport cost for the cost of the distance square, is a sort like horizontal distance that are like computing how much mass you should transport in the direction X from one place to the other. So just to give like an extreme example, why maybe the Wasserstein distance make a little bit more sense. So imagine that like F is a bump, and G is simply a translation of this bump. So the L2 distance between F and G is basically the sum of the areas, right? Square. So basically, if you think about in metric terms, so this distance is basically telling you that F and G are completely far apart from each other because they have like a disjoint support. While if you compute the Wasserstein distance between those two, the Wasserstein distance is going to give you something that is proportional to the distance between those two. So in that sense, this gives you a horizontal distance, while the L2 distance gives you like a vertical distance. So this is some sort of intuition to have, and that's why, for example, it makes a lot of sense while comparing histograms. And of course, like if you do convex interpolations, so imagine that you are considering the purple one is the distribution F, the yellow one is the distribution G, and you do basically a convex interpolation using the L2 distance, you see something that is not supernatural, that you are basically like creating and destructing mass. So there is not like a very nice geometry when you interpolate to one to the other. While when you do interpolation in the Wasserstein geometry, so in this optimal transport geometry, you see that like you have a very natural geometry for this space of measures, or for this space of histograms. So that is like in a very high level, in a very intuitive level, like why consider this type of distance makes a lot of sense in certain applications. So you may also be familiar, like other than L2 and other than the Wasserstein distance. So you also see in many machine learning applications that like the loss function that we consider is the relative entropy. So in light of the L2 and the Wasserstein distance, so like what is the main difference? So this is a very nice tweet of Gabriel Perret. So Gabriel Perret do a lot of nice tweets. So he's a mathematical influencer that I should encourage you to follow. So like if you follow, okay, so and this is one of those. So like what is the idea of the entropy? So here we are defining the entropy. Let's look in the discrete case. So the entropy here is the physical entropy. So like is with the minus sign. So then like how should we think intuitively about this? So like more sparse, more distributed, like your data is, higher is the value of the entropy. So for example, here you have like the extreme case when the entropy is 0. Here you have a middle case, and here you have like the other extreme case when the entropy is high. So in the continuous case, like you could think about the entropy has like the relative entropy between a probability distribution and the Lebesgue measure. So, and basically, like more distributed, so more closer to the Lebesgue measure, your entropy is going to be high, and more you are like a bump concentrated in a point, your entropy is going to be small. And if you think a little bit about the same example when you have like compact supports, so if you compute the relative entropy between F and G, here there is a problem. So this is like F divided by G log F divided by G dx. So in particular, what you see is that since F and G has compact support, they are disjoint. So basically, the entropy values plus infinity, because like in the region where F exists, G is basically 0. So like when you compare the relative entropy between those two distributions, like the KL divergence or the relative entropy tells you that those distributions F and G are very far apart. So like this is like a kind of scenarios where it makes a lot of sense to use the Wasserstein distance. And like this remark was a very enlightening remark that appeared in one of the papers of like generative adversarial networks. So that basically the contribution of this paper was changing the loss function that introduced by Ian Goodfellow, that was the relative entropy, by the Wasserstein distance. And the main argument was a very similar argument that I present now. So they say, consider two sets of probabilities. So one, that is a probability in R2 concentrated in this line. So the line when x is equals to 1. So it has probability 1 if I'm in this line and 0 otherwise. And now consider a shift of this probability. So you have now a parameter theta that you say it's 1 if I'm in this line, in the red line, and 0 otherwise. So since those two families of probability has disjoint support, if theta is different than 1, I'm sorry, so here has a typo, so theta should be 1, not 0. So if theta is equals to 1, the Kullback-Leibler divergence is basically 0, and is plus infinity otherwise. We could also remedy this fact that the relative entropy is plus infinity by considering the Jensen-Shannon. But anyway, we have still like this binary case where we are going to get 0 if theta is equal to 1 and log of 2 otherwise. So regardless of the distance, regardless of the theta that I use, like the Shannon-Jensen or the Kullback-Leibler, is going to give me the same result. And this is very counterintuitive. So this is not exactly what we want. So what we like is that like if I compute the Wasserstein distance between those two distributions, this gives me basically the distance between those, the modulus of the distance between those. Okay? So this is just like a very overview on like some very intuitive ideas. And now I would like to move a little bit more on the computational side and also like in a little bit of theory. So the question that we should ask now is, okay, very nice. The optimal transport problem has very nice features, in particular when my cost function is given by a distance. But how do I compute it? How do I compute this problem? So and by computing, I'm interested in both. So I'm interested in computing what is the best coupling gamma, so means the gamma that is the argmin of this variational problem. And also like once I have the coupling gamma, I can also compute what is the minimal value, what is the distance in this case, okay? And for this, so we enter what is like, we are going to spend some time this week talking about the entropic regularization of optimal transport. So this was just a warm-up. Now is basically where we are starting. So is there any questions? Not all of you are sleeping, so I'm very happy. So this is a good sign. So what is the idea of the entropic regularization? So we start as before. So we have here a cost function. So this is basically the Monge-Kantorovich formulation. The only change that I'm making is now that my probability distributions are not anymore mu and nu. And from now on, I'm going to denote it by rho 1 and rho 2. So my data is I have rho 1, rho 2, two probability distributions. For me, X and Y are Polish spaces. If you don't like Polish spaces, or if you are not familiar with Polish spaces, think that X and Y are like subsets on RD or simply RD itself. So and what we do is we take the Monge-Kantorovich formulation and add an entropic term. So you basically add plus epsilon, that is a regularization parameter, integral of gamma, log gamma. And like we need, so since we are in the continuous case, we need a reference measure. Since the measure that we have are our data, ρ1 and ρ2, so then I take like the relative entropy between gamma and ρ1 and ρ2. So I'm being a little bit lazy, so I'm writing simply gamma, but you should understand gamma like has a density with respect to the product of ρ1 and ρ2. So gamma is the Radon-Nikodym derivative with respect to ρ1 and ρ2. So in this setting, so again, nothing changed. So the set of couplings is compact for the weak star topology, is a convex set. We needed to do a little bit of work to show the lower semi-continuity of this functional, but like this is something that we do. This functional is lower semi-continuous. And since this morning you learned with Silvia Villa, so you can also verify that this functional cost plus entropy is strictly convex. So and since it's strictly convex, there exists a unique minimizer. So since the minimizer exists, thanks to the compactness of the set of coupling and the lower semi-continuity of the cost plus entropy, so the minimizer is unique. And this is very nice because you learned this morning that not always when epsilon goes to 0, we have uniqueness. So there are some cases that like there exist more than one minimizers. And the work that we needed to do in the following is that like not only the minimizer is unique, but you have like also a characterization of the minimizers. So the minimizers are given by gamma epsilon, and it can be decomposed by a function of x times a function of y exponential of minus c divided by epsilon. So like is a sort of like a Gibbs energy on this like epsilon of minus c divided by epsilon, but you have like those weights A and B that ensures that gamma has the correct marginals ρ1 and ρ2, that gamma is a coupling of ρ1 and ρ2. So like to show this characterization, so to show that the function is strictly convex and then there is a unique minimizer, so it's not a lot of work, but like we are going to spend some time in proving this characterization. So how should you think about the effect of the entropy? So this morning, Simone introduced the discrete case. So imagine now that like you have two measures, so two discrete measures. One, the ρ1 is given by the red dots, and the ρ2 is given by the blue dots. So when epsilon goes to 0, you know that the solution is basically a permutation matrix. So every point is matched, every point in mu in ρ1 is matched to a point in ρ2. So as much as the epsilon increases, you are adding a little bit of noise. So you are adding a regularization. So you allow interactions between different points. So now when epsilon is equal 1, for example, you see that like all points not only interact with one, but like with many of them at the same time. So, and of course, like when epsilon goes to 0, you expect, and this is something that we should do tomorrow, we show that like when epsilon goes to 0, we are converging to a minimizer of the optimal transport problem, for the optimal transport problem without the regularization. Yes.
Or there are, I missed the motivation.
Very good. No, I didn't get into there. So one, it's nice that you have a unique solution. You have a characterization that we needed to prove, and we can take advantage of this regularization to build computational algorithms. So the first motivations are like computational algorithms that I'm gonna go to this in a second. The second motivation is when epsilon goes to 0, the optimal, for example, if you have the distance square, the optimal transport plan or the optimal transport coupling is concentrated in a map. So it's a singular measure in the product space X and Y. And here, this is a much nicer object because this is absolutely continuous in the product space X and Y. So like it's a much nicer object to handle. And that's why it makes a lot of sense also for computations. So I don't know, I will try to convince you all that this is like a reasonable formulation to look at, and those are really the advantages of the entropic regularization. Yes, good guys, questions?
Yeah. When we go back to the Kantorovich problem, we have an intuition of it, of the formulation, but about the last formulation, OT of rho 1 and rho 2. What's the intuition behind the formula?
So you mean like a geometric interpretation of
Maybe more intuitive than just.
so I mean, so if you want
not this one, the following, like the last one.
Of course. So you mean like here you can think about in terms of a transport map.
Yes.
So that I'm sending a transport to the other. I love this question because it's the next slide. So imagine now that you are looking like mu is this orange cloud, so it's a cloud of points, and rho 1 is the orange, and rho 2 is the blue. You are like transporting, but you have also some noise. So instead of like going in straight lines from one to the other, if you want to do interpolation, for example, what you are basically moving is through Brownian bridges. So this epsilon is a sort of like adding a Brownian motion to each one of those points. So you see that like when the Schrödinger bridge temperature is basically a different name for epsilon. So you see like when epsilon is small, like this cloud goes from the orange to the blue in a very linear way. And when epsilon is big, you have like some noise that is added to the problem.
Yeah, but that's the explanation for gamma epsilon. But
yes,
about the initial
the one to the top.
Yeah, with gamma log gamma over.
Okay, no, this I say in a second. Thank you for asking. So what I'm saying that like we can rearrange this guy, you can rewrite these terms in this one, and this is basically like the Kullback-Leibler of gamma with respect to this Gibbs energy, so exponential of minus c divided by epsilon. So you can write like the entropy regularization of optimal transport really has a regularization of the Monch-Kantorovich problem, or alternatively, you can write this as epsilon, the Kullback-Leibler of gamma with respect to exponential of minus c divided by epsilon.
Okay, and rho 1 and rho 2 are just here for the constraint.
No, rho 1 and rho 2 are the constraints,
yes.
But it's also the guide that I use to write the integral of gamma. So I need to choose. I need to write integral of gamma, for example, gamma log gamma dx dy, if x and y are like in real spaces in RD. But if x and y is not in RD, are like, I don't know, in a manifold, I need to use the volume of the manifold. Since here, I'm assuming that x and y can be a completely separable metric space, so a Polish space. I don't know necessarily what is a natural measure to include there. Then I use rho 1 and rho 2, because this is the measure that is given to me on my problem, in my data. Okay. So this is an excellent question. Since like in my space x and y, I may not have necessarily a natural measure to put there where I could integrate the entropy. I use rho 1 and rho 2, that is my data. Okay. But I totally agree with you that like if x and y is a real space, I could, instead of doing gamma log gamma, I could do dx then y. And I'm going to make a remark what are the relations of those two problems, how they are linked to each other. But excellent. Thank you for insisting, because I didn't understand in the beginning. Thank you for the nice questions. Other questions? Keeping asking questions because you are making me very happy. So, and I'm not sleeping, as you can see. So this is very successful. So why? So that is very nice. So let's look a little bit like what is the effect of epsilon on the gamma that is the argmin of this functional. So here what I'm plotting. So imagine that like you have one-dimensional distributions. We are in R. So rho 1 is this blue distribution that is a Gaussian. Rho 2 is like those two bumps that are like a mixed Gaussian. And what I'm plotting here is gamma epsilon that is the argmin of this problem, the entropy regularization with different values of epsilon. So when here I have epsilon very small, so you really see for the distance square, for when the cost is the distance square, so you really see that this gamma epsilon is very close to a map, so I'm very close to the Monch solution. And as soon as the epsilon increases, I'm going to a regime where I get like a absolutely continuous distribution, like with a reasonable density. So this can give you an intuition that like when epsilon increases, you are interpolating between the minimizer of the Monch-Kantorovich formulation of optimal transport, this one, to the minimizer of the relative entropy of gamma with respect to the product rho 1 and rho 2. And like it's not a really hard computation, like you can think a little bit that the one that minimizes these functions is precisely when gamma is equal to rho 1 times rho 2. So this is what you are seeing here. So the minimizer, when epsilon goes to infinity, is basically given by the product between rho 1 and rho 2. Okay? So this is to have an intuition, like how So this was like an intuition, how the entropy affects at the level of points, at the level of the points in the support of ρ1 and ρ2. This is an intuition on how the entropy, so how increasing the epsilon, affects the argmin, so the gamma that minimizes the entropic regularization. Okay? So coming back to the point raised by Silvia Villa, so why is nice? So I have here gamma epsilon. I have this very nice shape that we needed to prove it. So I didn't prove why gamma epsilon can be decomposed by a function of AB times exponential of the cost minus C. But like if I use two facts, so if I use that gamma epsilon has this shape, so A and B also depends on epsilon. And I also use the fact that, like, by definition of my problem, the minimizer should be a coupling between ρ1 and ρ2. If I basically write the integral of gamma epsilon with respect to ρ1, this gives me 1. And if I integrate with respect to ρ2 in y, this gives me 1. So if I substitute the shape of the minimizer that is given by A times B times exponential of minus C divided by epsilon, I basically get the system. Yes?
Just to check, because I have a very, I mean, I'd say physical intuition, but I want to understand if it's right or it's just something in my mind. Is it, I mean, is it fair to say that you are letting, I mean, there is this analogy that comes to me, to my mind from quantum mechanics, which is to me very, very, I mean, I find it pretty interesting. It's the fact that you are kind of, in the case where epsilon is big, you want your distribution to describe something which is a separable state, so something which is the tensor product between two different states. And the more you decrease the epsilon, you are letting an entangled state of your system to be a solution. Is it something that makes sense or no?
I would say, like, if we have like a density matrices, so if you were like in a different context, I would say that we could talk about entangled.
Okay.
But here we are dealing like with very classical systems. So what we can think, like, if you want to think like in statistical mechanics terms, think that like if you give a position X here, what you are telling here that like there exists a unique Y when epsilon equals to 0 that is coupled with this X. So I can say that like this is a sort of deterministic. Every X, there is just a Y, one unique Y. So as soon epsilon increases, you add a little bit of noise, you add a little bit of randomness. So you lose the determinism because every X has a range of Ys that can be coupled. So if you want, like, you are adding
no,
a little bit
I think I said something which is point. No, okay.
So I would not say entangled, but you see, it's very close. You know, you add some randomness.
Yeah.
But in that sense, so I guess what you had in mind,
you're tuning the noise of the system.
Exactly.
Somehow. Okay.
So I mean, like, you can think that you are like in a sort of statistical mechanics regime, not really in a quantum regime. So, but that is the idea.
Okay.
And like, this is precisely a Gibbs entity.
Okay, no, from a statistical mechanic point of view, it's super clear. Okay, just thank you.
Very good, very nice the questions. Okay, guys, feel free to interrupt. Very good. Like, I'm very happy that you guys are not sleeping. So going to this, so using the fact that gamma epsilon has this very nice characterization, plus the fact that gamma epsilon itself is a coupling between ρ1 and ρ2. If given ρ1 and ρ2, we wanna discover who is gamma epsilon, the only thing that we need to do is to solve for A and B. We just need to discover who A and B is. Do you agree? So C is given, ρ1 and ρ2 is given. So to determine gamma epsilon, we just need to determine who is A and B. So and to determine A and B, now we know that we just need to solve this system. But this is a very linear system. And in general, we cannot solve it analytically. So there are very few cases that we can solve it. I may come back this to later, but for example, if ρ1 and ρ2 are Gaussians, we can compute analytically who are A and Bs. So then we can solve the system and get an analytical solution for gamma epsilon. But in general, we cannot do this by hand. So this is like, there exist explicit solutions when you have the cost, that is the distance square, and rho 1 and rho 2 are one-dimensional or multi-dimensional Gaussians. But in general, this is not very easy to solve, and you need to compute this numerically. And there is a very natural algorithm that is called the sinkhorn algorithm. So in how the sinkhorn algorithm works, and you see how simple it is. So basically, the sinkhorn algorithm takes advantage of this system of equations. And what you do, you initialize A and B. Let's say they are identically equals to 1. And then you define iteratively sequence an and bn by basically taking bn, and you divide this integral passed to the other side. So you compute bn using the previous an. So use the an minus 1. And then you compute an using the first expression on the top, just to divide the integral in the other side. And you compute an, use the bn. So it's a very simple algorithm. You can implement it in few lines, so in a handful number of lines. Since you express your desire to do some lab work, so we may do this tomorrow. We may implement this numerically tomorrow to get a feeling how does it work. And like, we know a lot of stuff about this algorithm also from the theory viewpoint. So we have like different settings for theoretical guarantees of convergence. So first, this was proved by Sinkhorn in 1964 in the discrete setting, also revisited by Franklin Lawrence. And like in the continuous setting that I'm discussing now, this was like proved first by Ruschendorf in 1995 and by Chen, Giorgio, and Pavon, more recently using different types of techniques that like more closer to Franklin Lawrence approach. And also like, you know, that there are results saying that like this entropic regularization, the Sinkhorn algorithm, like approximates optimal transport distance in linear time. So I'm not gonna enter a lot into details about like the different formulations of Sinkhorn algorithm or different viewpoints of entropic regularization of optimal transport. So for example, the dynamical formulation, the link with large deviations, or also like has a stochastic control problem. So if you are interested in those aspects, I really advise you guys I encourage you guys to look to two very nice surveys. So one by Christian Leonard and another one very, very recent from Chen, Giorgio, and Pavon. If you are more interested in the numerical part and like the different types of Sinkhorn algorithm and how Sinkhorn algorithm appears by different names in different contexts of mathematics and computer science, there is this very nice review by Martin Indel that I cannot encourage you more to do this. So like the goal of at least this part of this mini course is like to understand a little bit how the Sinkhorn algorithm works, both algorithmically and theoretical, like prove theoretical guarantees of convergence, and provide a little bit an understanding why the minimizer of the entropic regularization has this shape that is on the top. Okay, that is my goal. Try to prove all the results that I have just mentioned here. Okay, questions? Is it okay? Clear how the algorithm works? Because now we start the theory. So let's say now I start the more theoretical part. So like we are going to develop. So today, I hope to advance a lot on this duality approach for the channel entropy regularization of optimal transport. And then in the next days, we talk about the convergence proof of the Sinkhorn algorithms. And if time remains, we also talk about some applications. Okay? So now I'm going to talk a completely different story. So I introduce you the entropic regularization using like a regularization of the Monge-Kantorovich formulation. Now I'm introducing which is a priori a completely different problem, but then we are going to make a link to this problem that I have just discussed. So and what I'm going to do like is a completely different functional, or a priori a very different functional, and let's see how does it work. So like here I'm fixing the setting from now on, and you see that from now I'm going to be a little bit more precise. So X and Y are Polish spaces, so completely separable metric spaces. For here and now on, C will be a bounded function. So to make this setting, to do like some theorems and simplify some of the proofs. So like we are always working on C, a bounded coast. Rho 1 and rho 2 are probability measures. and epsilon is always a positive parameter. And now we introduce the dual functional. So given u and v, two functions from u from x to r and v from y to r, you define the dual functional d epsilon by the integral of u with respect to ρ1 plus the integral of v with respect to ρ2 minus epsilon double integral, so the integral in x and y of exponential of u plus v minus c divided by epsilon integrated to d ρ1, d ρ2. So in what we are interested now is like to a maximization problem. So you want to compute the max of this functional where u and v are in very suitable spaces. So like those spaces, Lexp is just a technical condition that, let's say, is the most general space where my dual functional is well defined. So I'm just asking that like those potentials are measurable functions and that the integral of exponential of the potential with respect to ρ1 or ρ2 is bigger than 0 and is well defined, it's finite. So this is it's just a technical condition. We see that thanks to the assumption that C is bounded, we can really get rid of it. But this is the most general setup that we can work. Okay, so what we want is to found the maximizer of this problem. So if you came from the numerical viewpoint, you may like much more this problem than the previous one that I showed you, because this maximization is a maximization without any constraint. So in the Monch-Kantorovich formulation, we have the constraint that gamma should be a coupling between ρ1 and ρ2. So anytime that we do an algorithm, we need to ensure that this constraint is realized. So if you are from a numerical analysis or you are thinking about numerics, this problem is much nicer. So we don't have any constraint, and with a little bit of work, you can show that this functional is strictly concave. So you, for example, also experimentally could try to solve this problem using the stochastic method or gradient ascent. So it's not very complicated to implement. However, from a more theoretical viewpoint, this poses some problems because to prove the existence of the maximizer is not at least obvious how to get compactness of the maximizing sequence. So what we want to do, we want to take maximizing sequence for this problem, have some sort of compactness, or extract subsequences that are convergent, and then prove the existence of the max. And since we have an unconstrained problem, this is not very clear. So and to get this compactness of the maximizing sequence, we need to introduce this entropic transform. Let me save one on the blackboard, because this expression will be useful for the following. So given u, that I'm going to call a potential, so I define the C epsilon transform of u, or the entropy transform of u, has minus epsilon log of integral of exponential of ux minus c divided by epsilon, and I integrate in d ρ1 of x. So I'm integrate in ρ1 of x. I have here a function of x and a function of x and y. So when I integrate it and take the log, this gives me a function of y. Okay? So given u of x, when I compute the C epsilon transform, this gives me a function of y. Good? So if you can think about this has a sort of a soft mean. I always make so a soft max or soft mean. So has a way of or if you use a way of regularize the ReLU. So this is a way, but for now, this is a C epsilon transform, and why we call C epsilon transform will be clear tomorrow. So, but just let's assume on it. And why we like the C epsilon transform? Because if you fix one of the potentials, let's say you fix the potential u, and you apply the C epsilon transform in u, you know that you are always increasing the dual functional. So given u and v, if you apply the C epsilon transform in u, you know that the function of u C epsilon transform is always bigger than the epsilon of u and v for every v. And in particular, they are equal if and only if v is equal to the C epsilon transform of u. So this is a very nice computation And this gives you a little bit of intuition. How does it work? So like, let's write the dual functional as before. And now we apply Fubini. So in this, we keep this expression fixed. So in this one, what we do? We first integrate in 0,2, and then we integrating in 0,1. So let's do some massage on this formula for the C epsilon transform. So I just pass the minus to the other side. So I can write this as exponential of minus u divided by epsilon. So I also took the exponential, so I have no more the log. So I can write this C epsilon transform equivalently using this expression. So and then I recover that what is in here is precisely the exponential of minus u C epsilon transform divided by epsilon. I recover. So, and then what I know? So since now I'm integrating only in row 2, I substitute this expression to what is on the blackboard, and I get basically this formula. And what we learn here, we know that like for any v, I just show that the epsilon of u and v is bigger or equal than the epsilon of u and u C epsilon transform, just by verifying that this function g is strictly concave and attains its maximum when t is equal to a. So in this case, when like v is equal to the u C epsilon transform of y. So this is a very nice computation that basically what teaches you. So imagine that you wanna maximize the epsilon, so you keep the first variable u fixed, and now you take the argmax with respect to v. So this argmax with respect to v is precisely the entropy transform or the C epsilon transform of u. So if you wanna get an intuition about what the C epsilon transform is doing, is like basically a block coordinate ascent of one of the variables. So if you fix u and optimizing v, this is precisely what you get for the C epsilon transform, and the reason for this is this computation. Is this okay? Look, if it's fine, I don't know if I'm doing too fast or too slow. So how is the speed? Too fast. So let's do. So, okay, I do a little bit slower. So what we are doing is dual functional. Second line, I'm just applying Fubini. So I integrate first in row 2 and then in row 1. So when I integrate in row 1 and row 2, this expression here is just a massage. What is the definition that we give by the C epsilon transform of u? Then I substitute here exponential of minus C epsilon transform divided by epsilon, C epsilon transform of u. Then this is just an integration in row 2. I put those two terms together, and then I verify that this guy is strictly concave with respect to v, and attains its maximum when v is equal to the u C epsilon. And this is just a verification, just verifying that the second derivative of this guy is strictly positive, and actually the minimum is when, so the maximum is when t is equal to a. Okay? Strictly negative, sorry, yes, because it's concave. So I missed the analysis one. Okay, good. So, and like the intuition is what we are doing. We are defining the C epsilon transform that is basically taking the argmax in one coordinate, keeping the other fixed. Okay, and that's why we get the first line. And of course, the proof works in the same way. If instead of taking the C epsilon transform of u, I take the C epsilon transform of v, so you can write a similar statement. So this works for both. Okay? And okay, in particular, those two guys are equal if and only if v is the C epsilon transform of u. So let me see how far I got. So very good. So I'm very happy. I'm not very happy that you stop you asking questions. So this is not a very nice sign, but please interrupt me. So now what we do? So now we get some some regularity properties of the C epsilon transform. So that is the key. So like if I assume that C is a bounded coast, what I can show is that the C epsilon transform of U is also a bounded function. So since it's y, so I'm stressing that this is y. So it's a bounded function with respect to rho 2. And the same, the C epsilon transform of V is also a L infinity function. Yes, Pablo? Previous slide.
Sorry, just wanted to ask on the previous slide when in the dual the last integral, should we integrate in this measure rho2 times rho1 times rho2? It's not. It shouldn't there be just Lebesgue measure?
No, very good point. So like we are integrating with respect to rho1 and rho2, and now you look that this integral with respect to rho1 is basically equal to exponential of minus C epsilon transform of U divided by epsilon.
So it's right measure, yeah, not Lebesgue one.
No, like you can choose. So since here we choose to use the integration of this guy with respect to rho1 and rho2,
okay,
then we keep. But like we could do a similar computation if you are in RD choosing dx dy.
Oh, okay, thank you. No,
okay, very good. No, that is very good. But like I'm not talking about this. This is something that we check later. How does it work if I choose a different measure to integrate? Okay, yes.
When we observe this computation, it means that at the end we can rewrite d epsilon just as a function of one functional, no? Because of the relation between u c epsilon and v c epsilon.
Yes, you see here I have u, v, and u c epsilon. So I still need the two functions. I still need the u and v. So I still need both of them. But,
yeah,
what
u and v are related, no?
By this computation, so I cannot write real has a equality, but I can show this inequality. Okay. You know, like I cannot show that I can show that the equality holds if and only if v is related to the C epsilon of u. So you should be careful. Okay. It's not like maybe you are familiar when epsilon equals to 0, that you can really do what you are saying. But in this case, we have one inequality, and then you have the equality if and only if v is equal to the C epsilon transform of u.
But what's the difference between the case in which we have epsilon equal to 0 and epsilon?
Okay, this I may ask you to have a little bit of patience and wait tomorrow. Okay. So when we finish the analysis with epsilon positive, we can go a little bit more and make a parallel with, I don't know if you, Simone, want to add something, but I guess it's better to...
Yeah, so we'll answer tomorrow to this question, but maybe, so it's true that via this idea, you can say, okay, instead of doing the soup with respect to every u and v, I just do the soup of d epsilon u c epsilon just with respect to u. You can do it, but it becomes more complicated as a problem because now is a function which is concave with respect to u and v, but it's not concave with respect to u if you write u and u c epsilon, or at least it's not apparent. So sometimes you can do this kind of substitution and you are lowering the number of unknowns, but the problem is not nice anymore because you lost a bit of the structure, if this makes sense. So the idea is to keep the variables u and v and you update one of them and the other. But you are right that you can write it as now just the soup on u and you substitute v equals u c epsilon, but in a way it's a different problem from the optimization point of view, right? So in one sense you're doing, okay, I'm doing the optimization in x and y. In the other case, you are doing one optimization in y, and then you do just an optimization of x, but the functional is completely different now.
But do we have the same results at the end?
The maximum will be the same, but from the point of view of showing the, I don't know, the convergence of the algorithm or properties of the minimizers, it's different. It's a different, so maybe there is a way to look at it and you can prove the same thing, but it's more natural to you to stay with the u and v. So I don't know if...
No, it makes, yes, so, and that is what we are going to get. So like, what is our goal? Just to put the feet on the ground So like we want to show that like the dual problem has a maximizer. So what I call dual problem is this supremum, so that the supremum is really a maximizer. So when I want to show that this guy has a maximum, and what we learn from the previous theorem is that like if I apply a C epsilon transform in one of those functions, I'm increasing the value of this maximizer. So by increasing, I'm doing a little bit better. So I fix one variable and I optimize the other. And this is precisely what the C epsilon transform is doing. So let's see, we are going to get in there and you see how those things are related. So you have a good intuition, but let's write this calmly. So, okay, so now what we need. So we have this result that by applying the C epsilon transform, I'm increasing the value of the dual functional. Now I need some regularity of these C epsilon transforms. That regularity is what allow me to get some compactness. So what is the regularity results that you get is that like you assume some regularity for the coast C. So for example, suppose that C is bounded, so it's a bounded coast with respect to X and Y. Then we can transfer this regularity of the coast to the regularity of the C epsilon transform. So like the U C epsilon is going to be bounded with respect to Y, and the V C epsilon is going to be bounded with respect to X. And the same, like to show that like the C epsilon transform is well posed in this LX space, I also show that like those potentials belongs to LX. And a very technical aspect is like there exist the constants like lambda U C epsilon plus lambda U. This is always bounded in L infinity by the cost function C. So let's see how we show the first part. So the first part is just like a straight computation using the fact that the coast is bounded. So you start with a function U in LX. Then by definition, the C epsilon transform is given by this expression. So now let's use the fact that C is bounded. So like I can bounded C by its L infinity norm. So since the L infinity norm is just a number, I can take the L infinity norm outside the integral, use the property of the log, that the log of the product is the sum of the log, and then I get C, the norm infinity of C minus epsilon log of this integral that is basically the definition of my lambda. So lambda U is by definition minus epsilon log integral so this is just a number, right? So like I'm integrating a function in X, in dx, in the rho X. So this is just a number. And since we assume that U is in LX, I know that this guy is strictly bigger than 0 and is finite. So this quantity lambda U is always a finite number, is always well defined. So here what I show is that like, so if C is bounded, the U C epsilon is bounded from above. Now, a similar computation also tell me that the C epsilon transform is bounded by below. And here, like instead of getting a bound that I have plus the norm L infinity, I just get doing exactly the same computation minus the norm L infinity minus my lambda U. Okay? See if this compiles, if this computation is okay. So since I'm taking the L infinity norm, is exactly, I just skip this passage. So it's a number, so I can take out of the integration, and I use the property of the log that like the log of the product is the sum of the log. Okay, very nice. So this is very nice because here what we are learning, if I assume that C has some irregularity, so for example, is bounded, this transfers to the regularity of the potentials as well. And the second one is more like a direct computation. So to show that this guy belongs to the LX, I need to show that this quantity is positive, so it's bigger than 0, and it's finite. So then I take exponential of the U C epsilon transform divided by epsilon. By definition, and by using the fact that C is bounded, I can get this expression. So this is finite by definition because U belongs to LX. This is finite because C is just a number, and I'm integrating 0, 2, so I get a finite expression. So this is just like a computation that you substitute and you do it yourself. Okay? So what else we can get? So in the same way, so this I'm just going to state, so we are not going to prove this. So it's basically like the philosophy. So if you assume some regularity on C, so for example now, if the cost C is L Lipschitz, so it's a Lipschitz function with like the constant Lipschitz equals to L, then also the C epsilon is a Lipschitz function. The second one is like you can also control the oscillation of your C epsilon transform. And something that may be important, like in probably tomorrow or in the last lecture, is that like if C is bounded, let's say for a constant M, then the C epsilon transform of U or the C epsilon transform of V, so the C epsilon transform of U is a one Lipschitz compact operator between L infinite of rho 1 to LP, for P in between 1 and a finite P. So this I give without a proof, but like this is the general philosophy. So assuming some regularity to C, thanks to the expression of the C epsilon transform, I can prove also some regularity to those potentials. So let me show just one, just the first one to give an idea. So assume that U is in LEXP, and like without laws of generality, take 2 points y1 and y2, and assume that like the C epsilon transform of 1 in y1 is bigger or equal than the C epsilon transform in y2. Of course, exchange y1 and y2 and works in the same way. So we want to show that like the C epsilon transform is a Lipschitz function with respect to y. So take the difference between the C epsilon transform of U of y1 and y2. So this is by definition those two expressions, where the only thing that I'm changing that like in the first, the cost function is y2 because of this one. And in the second one, the cost function is in y1. Remember, we are integrating in rho 1 that is a function of x. Then what we do? Then we do the trick of like summing and subtract the same quantity. So here I have the cost of x, y2. So I just subtract c of x and y1 and add c of x and y1. So I'm just adding 0. But thanks to this, here appears some sort like here I can use the Lipschitz continuity of the cost function c. So now here I can use that the hypothesis that like my cost is Lipschitz. And by using that the cost is Lipschitz, so I can basically write this guy has smaller or equal than L times the distance between y1 and y2. Again, use the properties of the log. Log of the product is the sum of the logs. Those two guys is going to cancel out. And I end up just with the condition that the difference between those two guys is smaller or equal than L, the distance between y1 and y2. So what is this distance? So this is the distance in the space Y. So Y is a metric space with a distance D. Okay? Those are like nice computations to see once. And so now I guess we have like everything on the table. Yes. Say again.
Yes.
How did you notice there is a problem on Zoom? Because you watch my presentation. You are not looking me here. You are looking me on the screen.
I see you better.
So I don't like me in person. So you look on the unbelievable, Andrea. So this generation of like Zoom lectures are terrible. Like, so you get so used to have like Zoom lectures that now you cannot. You are not comfortable with real people. Yes, please. Thank you. Of course, that's what.
Yeah,
here or the previous one?
Perfect. Yeah,
very good.
I'm not quite getting the point 3. Like, what does it mean that it can be seen as an operator from L infinity to Lp rho 1?
So, I mean, you can. So this is an operator, right? So
Yeah.
I'm giving you like a function defined between two functional spaces.
Okay, but the function is like is this one, right? So if you take okay, so if I take as an arrow one, maybe it's because I'm not a mathematician, so like for me it's not trivial to see.
I don't know
This
what
is
I
not
can. How can I? So you can think this in that way. So I'm writing u directly. So very good. important.
Okay,
So
sorry.
this is a functional of u that like I can apply in a function y.
Okay. Okay. Okay.
So what I'm
Okay.
saying, like that this is an operator. I guess probably the answer is in the first line. The
Okay.
proof of this is not obvious. I guess the proof of this is like probably the hardest thing that we show up to now. So that's why I'm skipping. So here there is like something non-trivial to prove, but like that this is an operator. I guess you can think in the first line.
So it's
so you are feeding u, no? So if C is bounded, so we know that the C epsilon transform is a bounded function. So I'm feeding u, and this in the end of the day, what it's saying is that like this goes to L infinity to LP.
to LP of
This one limits.
Okay. Okay. I think I'm starting to see this. Okay.
Good,
Thank you.
no, very, very good. So other questions, because like we are not doing a break, but the questions can be seen as a break. So, okay, so I guess like we have everything on the table to do what we were promised to do. So like now, under the same hypothesis, so like I have X and Y completely separable metric spaces, and C is a bounded cost function. Mu, rho 1 and rho 2 are probability measures. So basically the result is that the supremum is actually a max. And this is attained by unique couple, U0, V0, and unique up to a translation. I make this clear in 1 second. And in particular, we have that like U0 and V0 are in L infinity. So since my cost is bounded, I can also show that the maximizers are also bounded. So, and why I have uniqueness up to translation? So if you take A, like a scalar, a number, you can see that like by adding and subtract this constant. So remember, you have like integral of u plus a d rho 1 plus integral v minus a d rho 2 exponential of u plus a plus v minus a divided by c. You can see by just writing down this functional, like by just writing down the epsilon u plus a v minus a, that like actually by adding and subtracting the same constant, this, so the function, like the value of the functional does not change. So this clearly does not change because I'm just adding. So d rho 1 integrates to 1. So I'm just adding a minus a. And here also clearly does not change anything because I'm just taking a minus a. So like by adding and subtract a constant, I don't change the value of the epsilon. And this is a little bit annoying when you are getting the compactness. But like there exists one mu0 v0 that is a maximizer up to these trivial translations, and those u0 and v0 are L infinity. So what is the idea? So for this, we are going to use a lemma that I guess go in the spirit of your question. For me, wait, this goes really on the spirit of your question. I guess this is what you probably had in mind. So I'm not going to show this lemma, but like what this lemma is saying is, so there exists u star v star such that for every u and v, u star and v star, the d epsilon of u star and v star are always bigger than the epsilon of u and v. So like you are doing both at the same time, but you see there exists a couple, u and v. Those v star and u star are bounded by a constant and the L infinity norm of C. And moreover, there exists a A, so just one A, such that one U star is the C epsilon transform of V and vice versa with this constant A. So I can choose a constant A such that I can do this step at the same time. And one is the C epsilon transform of the other. So this is the thing that annoys a little bit to get the compactness, that here we needed to fix a constant A such that you get that one is related. So U star is related to V star via the C epsilon transform. But this is just the technical, just to get rid a little bit of the symmetry that we have on the dual functional. And like using this lemma, so here we go slowly, we get the existence of the maximizer. So how the argument works, so like we start, take UN and Vn, maximizing sequence. And what we do, so we basically take for every n, the C epsilon transform of UN and the C epsilon transform of Vn. So, or alternatively, so you use the lemma, and we know like that there exist UN and Vn that are in L infinity, such that the L infinity norm are both bounded by 3/2 times the L infinity norm of C. And this is thanks to the C epsilon transform. That is how I get the regularity on the maximizing sequence. So once I know that then my maximizing sequence, UN and Vn, are in L infinity, I can basically use Banach-Alois-Glue theorem to get two subsequents, UNK and VNK, that converge to U bar and V bar. So that is how I get the compactness. So Banach-Alois-Glue tell me that like, so here I'm not relabeling, so I'm not using UNK, so I'm calling NK equals N. So and since I have this convergence, now to show the existence of the maximizer, just follow like by the upper semi-continuity of the dual functional. So those are basically like linear terms. And here I have the exponential. And by taking the limit, I show that this guy, so the sup of U and V of the epsilon of U and V, so this is always smaller or equal than the limit on U and V. So and then I have the existence of the maximizers, and U bar, V bar are in L infinity. So it's really like we are using the direct method of calculus of variations. And what allows me to get the compactness of the maximizing sequence are really this hypothesis that I'm using, that the coast is bounded, and via the C epsilon transform, I can transfer the boundedness of the coast to the boundedness of the sequence UN and Vn. So you see, basically what I've done is like having you doing some a priori estimate using the idea of the C epsilon transform, and then applying Banach-Alois-Glue to get the existence of to get the subsequence, and consequently the existence of the maximizer. Good? Too fast? Questions? Yes.
So if you don't have a bounded cost function, what can you do to sort of get this or similar result?
So more general. So what I can say, like in 30 seconds, and I guess it's easy to believe, is that like if instead of assuming that the coast is bounded, you assume that the coast is Lipschitz, you can do a very similar argumentation, but you need to use Arzel-Ascoli or Ascoli-Arzel. I never remember the order. So you can do something like this. So go beyond that, you need to think a little bit. So this is not, you don't go in the same lines.
Okay.
So like you say, if you want to do, for example, for the distance square, no, right?
Yeah.
That is so no, you need to do a little bit of a different work. Okay. In particular, like you need to be a little bit more careful on the a priori estimates. So the boundedness helps a lot on getting like explicit estimates here. And if you want a sort of like textbook estimates approach, but like you could also think that like instead of assuming that C is bounded, you could assume C some integrability. I don't know, with respect to ρ1 and ρ2. And instead of doing this, you apply Jensen here. So you can use it like a sort of Jensen and get a little bit more refined estimates.
Okay.
But like to make the life easier, we are assuming that this is is bounded, so we can rely on Banach-Lagrange, which is typical what happens when you do classic optimal transport. So you first prove when C is bounded.
Yes. Okay.
But no, very good question. Very, very good question.
Thank you.
Other points? So I guess I have a 15, 20 minutes. It's 3:30, right? It's 1 hour and a half. Okay. So I needed to be wise on. So okay, let's go a little bit beyond. So now, okay, we study a completely different problem. So I start introducing the entropic regularization of optimal transport based on the Monge-Kantorovich formulation. And then I switch completely the approach. I say, forgot how I introduced the entropic regularization. And let's look now for a different functional that is basically I needed to maximize this functional d epsilon. Now, how this variational problem of maximizing d epsilon, how this variational problem relies to the problem with the couplings gamma. And this is basically given by the following theorem. So like we are in the same setting, so we have two Polish spaces. C now is a cost function. For this specific theorem, you don't need to assume any boundedness. Rho1 and Rho2 are probability measures. Then, for every gamma, we have the following inequality. So I'm just being short. Remember, epsilon Kullback-Leibler of gamma with respect to epsilon exponential minus c divided by epsilon is basically the cost of gamma plus the entropic regularization. So let me write this again. So it's just like a short notation to what we want. So we have C epsilon of gamma. So this is like integral of C d gamma. This is basically the cost of classic optimal transport, so without the entropy. But now I add the entropy. So this is gamma log gamma d Rho1, Rho2. And like, what is a simple computation to do? Just open the log is that this is precisely equal to the relative entropy of gamma with respect to exponential of C, and this is by definition epsilon, the Kullback-Leibler of gamma with respect to. So what we are saying there is that for every gamma, the cost of epsilon, so the C epsilon of gamma, is always bigger or equal than the dual functional plus epsilon. And we have equality if and only if gamma has this specific shape. And look, telling that gamma has this specific shape is exactly what we wanted. So gamma epsilon of x and y is like exponential of u of x plus v of y minus c is equivalent to say that here I have a epsilon of x, b epsilon of y, exponential of minus c divided by epsilon, where a of x is exponential of u divided by epsilon, and b of y is exponential of v divided by epsilon. So this is precisely what we want to get. So and you see, the proof is also very short. So how do we get it? So start with the cost, the C epsilon gamma. So this is precisely the definition, like in the blackboard. And now what we do is like we just add the 0. So we take two potentials u and v. So here I have the integral with respect to Rho1 plus the integral of v with respect to Rho2. And now I'm basically add minus u plus v integrated with respect to the tensor product of Rho1 and Rho2. Since u depends only on x and v depends only on y, what I'm doing is just adding 0. So this quantity is exactly the same than this one. So and now I just rearrange the terms. So I put C and gamma all together with minus u and minus v. So here, so the next line, I'm not doing much. I'm just passing what is on the end in the beginning and put this one here. And then I use this, and then I use the following, it's like I use a clever inequality so that I can write this part here has something that is bounded above of minus epsilon, this integral here. And notice that here I'm getting exactly the dual function of d epsilon. So here I get d epsilon plus epsilon. And basically the inequality that I'm using is basically this one, which tell me that I have the inequality and the equality if and only if t is equal to exponential of minus s divided by epsilon. So minus s here is precisely c minus u minus v, and t is my gamma. So t is going to be the gamma. So this we can verify by hand, this inequality. But if you are familiar with like the Legendre transform, basically what we are using is a sort of a French-Young inequality. What I'm saying that like the Legendre transform of the entropy is basically this Gibbs energy. So what we are using is like some property of the Legendre transform of gamma log gamma to get this inequality here. But otherwise, this is an inequality that we can use directly, and you can verify by hand that this holds, and you have the equality if and only if t has this shape. Okay, so here what we have. So we have that this guy is bigger or equal than the epsilon, and you get the equality if gamma has the specific shape that you are looking at. Okay? So and now I guess we are in position to state the like some equivalence. So like we have everything in hands to completely characterize the problem. So like under the same conditions, so like the cost is bounded, rho 1 and rho 2 are probability measures. So what we have is, so U and V, so U star and V star are maximizers for the dual problem. This is equivalent of the C epsilon transform of U is U star is equal to V star, and the C epsilon transform of V star is equal to U star. So if you assume too that U star is the C epsilon transform of V star and vice versa, you can show that the gamma star that is given by the exponential of U star plus V star minus C. Remember, gamma star is absolutely continuous with respect to the tensor product of rho 1 and rho 2. So if you choose this specific shape, we can show that gamma star is a coupling between rho 1 and rho 2. And if gamma star is given by that formula is a coupling between rho 1 and rho 2, you have the dual attainment. So you have that like OT epsilon of rho 1 and rho 2 that we introduced in the beginning is precisely equal to the epsilon in the U star, V star. So like so OT epsilon was basically the minimum of gamma, all couplings between rho 1 and rho 2. And we define this the OT epsilon of rho 1 and rho 2. So the entropic regularization of the Monge-Kantorovich problem between rho 1 and rho 2. And what we are saying that this guy is equal to the epsilon, U star, and V star. So I don't know, I may ask questions because I don't know if I stop here and do this proof next time because I'm going to take more than 10 minutes to do this. Or if at least I do a part now. So is there any questions for? No, it's not an error. It's just because of the computation. Like it's because of this computation here. So when I do this computation and I use this inequality, there is an epsilon that pumps out because of this inequality here. So you see like this inequality is always true, and I have this like minus epsilon to compensate. if you are like me, and I feel that you are like me, that this epsilon disturbs you, instead of taking the entropy, that is gamma log gamma, you could take like gamma between parentheses log gamma minus 1. So you see, like, you shift a little bit, is still convex, you have like a very nice properties, and then you can get rid of this epsilon. But this epsilon is just a number. And when epsilon goes to 0, this guy is going to disappear. So you get, you see that you get unexpected form in the limit. But you see, like, this epsilon came from the regularization parameter. But it shows up just because of a computation, so we should not be disturbed by that. So other questions? So I guess I'm going to finish with this theorem, at least the statement, which is the most important, that basically gives you a complete characterization of the dual problem and the primal problem. So basically what we are saying is that, like, the existence of the maximizers for the dual problem is equivalent to the dual attainment, and is also equivalent to the fact that, like, pi star given by this shape, so given by a function of a of x, b of y times exponential of minus c divided by epsilon, this is like the optimal coupling. So this all together gives all the ingredients that we want. So I probably like skip the proof. So we do the proof the next time that we are going to be in the morning. And I can make a comment, and then we are going to move to the convergence proof of the Sinkhorn algorithm or do some numerics. So, but I prefer to stop here. So we continue this the next time. You feel free to ask any questions. Or more questions that...
Thank you, meanwhile, to Professor Gerolin. Again, if you have questions, please ask them. Maybe meanwhile I switch on the lights before we fell asleep.
But I promise that, like, this was the first lecture that we introduced all the tools and did all the computations. From now on, we have everything done. So, like, from now on, things are going to be much lighter. But at least we play all the dirty game here.
Okay.
Yes.
I was not able to recognize it. So the dual problem is a convex duality. So you compute the dual in the sense of convex analysis.
Exactly. So if you compute if you want, like, the shortest way of telling that is, like, let me go to the first problem. So look to this guy. So we are taking the minimum of the relative entropy between gamma and this function exponential of minus c divided by epsilon. So if you compute the Legendre transform of this guy using the duality between measures and bounded functions that vanish at infinity, so you get precisely the maximum that I was showing before. So, and that is precisely the relation. So between, so these we are showing the relation between the relative entropy and the Gibbs energy. And this other term here comes by the fact that gamma is a coupling between rho 1 and rho 2. So this is linear. So, and if you compute the Legendre transform, you get precisely this expression here. So, like, the cheapest way of getting the duality would be compute the Legendre transform of the relative entropy, putting the constraints that gamma is a coupling between rho 1 and rho 2 has, like, a penalization. But here we can do everything by hand. So we start with the dual functional without any relation with the primal problem. The duality, in the end of the day, reduces to recognize an inequality. So we don't need to talk about Legendre transform convex analysis. So we can get rid of the convex analysis machinery by really checking an inequality in R. So we can avoid it. But basically what we are translating is the relation between the Legendre transform of this guy and the Gibbs energy.
Thank you.
Thank you for the question.
Okay, so I guess if you have other questions, you can ask him during the break. So we can do the break, and I will say probably 5 minutes or 6, 10, I don't know, some minutes before the beginning of the last last lecture. We go in Piazza dei Cavalieri to do a photo of the school, so that because now it's not raining. I don't know next days how it will be. Maybe it will be nicer. We do another photo, but for now it's good like this. So thank you again, Professor Gerolin, and coffee break.
In this second lecture, we will start to see how to tackle the convex case, so not strongly convex. And then we will go towards the non-smooth setting. So I will introduce some preliminaries on this. So this morning we have seen this point of view, the fixed point iterations point of view. And so we have seen that the gradient method can be interpreted as the fixed point iteration of a contraction mapping when F is Lipschitz smooth and strongly convex. So if we drop the hypothesis of strong convexity, so if we do not assume that F is strongly convex, then one thing happens, and the fact is that immediately this map that maybe I denoted by T gamma is not a contraction anymore. And indeed, there is this result that tells you that given F differentiable, if T gamma, so if there exists a gamma such that T gamma is a contraction, then necessarily the gradient of F is Lipschitz smooth, continuous, and F is strongly convex. So basically what we have seen this morning, so that this is all we can do. So if you hope that T gamma is a contraction, we will immediately get that, of course, sorry. So everything is always convex. So I saw the Simone's face that was not convinced. So in the convex setting, if T gamma is a contraction, for some gamma, then you can prove that the gradient of F is Lipschitz continuous and F is strongly convex. So basically, the analysis of this morning cannot be extended in any way. And so the idea is try to relax the assumptions on this T. And more precisely, what we will start to see is what happens if T is just non-expansive. So we will look at convergence properties of fixed point iterations for non-expansive mapping T. So we can still define this, and we start to see that there are some problems. So first problem is the fact that non-expansive mappings may have not fixed points. So one fix, so the, let's say, let's call it fixed T. So the set of fixed points may be empty. Maybe I do like this. So differently from the case where you have a contraction. And a simple example for this is a translation. For instance, you can take a translation in R. So in what follows, so in order to study convergence behavior of this stuff, I will assume that the set of fixed point is non-empty. Second point, even if the set of fixed points is non-empty, does not imply that the iterations are convergent. say xk is convergent. And the example here, one example, is the rotation. So if we take the rotations, for instance, of pi divided by 2 in R2 around the origin, then this is a non-expansive mapping. So, sorry, I didn't write the definition. Non-expansive means that is Lipschitz continuous with the constant 1. Okay? So, what I assume is just this. So, and the other example exactly is this one. So T from R2 to R2, that is the rotation of T divided by 2. So this will be, so if I start from an x0, for instance, this one, so this is the rotation around the origin. What happens is that I get this point, this will be x1, this will be x2, and this is clearly not convergent. Starting from this, there is an idea due to Krasnoselski-Mann, it's called. And the idea is the following. The idea is under relax. So instead of considering this simple iteration, you do the following small modification. So you start from a point x0, then you compute t of x0, and then instead of taking this next point, you take the segment between joining x0 to t of x0, and then you take a point somewhere here. That will be I want to put the right alpha, sorry, because otherwise, so it's the same, but I want to be consistent. So alpha t plus 1 minus alpha. Okay, and you have this point. This will be our next iterate. And now what happens is that if I do the rotation here of pi divided by 2, so I get t of x1, and I will take x2, which is okay, and you see what happens. For this specific example, this sequence converges to the origin. Okay, so this alpha is something between 0 and 1. And so what we will see is that iterations of this kind are convergent. And if you want more than this, the class, so instead of studying this modification, you directly give a name to two operators that have this form. So can be written as a convex combination of T, non-expansive, and the identity. So what do you do is that you define the class of alpha averaged operators. So E from H to H is alpha averaged if there exists a T prime, which is non-expansive, such that E can be written as alpha T prime plus 1 minus alpha the identity. There is a special case of this class of operators. That is the case alpha equal 1 alpha. So for if alpha equal 1 alpha, so if you have 1 alpha averaged operators are called firmly non-expansive operators. I don't. So I start just by writing a simple characterization where you just need to, this is a result of algebraic manipulations, so there is nothing. So the following are equivalent. So T is alpha averaged. So one thing, sorry. So in this convex optimization community, so T here in general is non-linear, but it's very common to avoid. So I will forget the parentheses, the brackets, okay, even if it's non-linear. Okay. So this is the first equivalence. And as you can see, so you have, let's say, if alpha, so if you don't have this piece, you would be non-expansive, being alpha averaged beyond this inequality, so you can subtract a positive term since 1 over alpha is bigger than 1, which is, and the inequality is still true. So it's something more than non-expansiveness. And the third inequality that is useful, especially in the case of 1 alpha averaged operators. This is the case where it is mostly used, is the following one. Okay. So this is almost never used. It is used a lot when alpha is equal to 1 alpha. And in this case, it is particularly simple because this term goes away. And so what you have is that it's correct. Is this one. So firmly non-expansive is equivalent to this. And for instance, so we will see examples of alpha averaged operators. So maybe the first example that I can do is that will be useful later. So if you take C, a closed convex set, then the projection onto C is 1 alpha averaged. So you can prove, you can use the last characterization. And maybe I can do now the fact, I can prove now that,
Projection as if you find the closest point.
yes, sorry. So yes, exactly like this. We will see that this is a special case of a more general operation you can do with the convex functions. So it is their mean of x minus y square, y in C. Okay. And then I wanted to show that even this is true. So, and the other example that is a proposition, maybe. So let's assume that F is convex and differentiable. Then the following is true. If you want, so the second is, write it correctly. So, should put okay. This is true for every x, y. And basically what it means that if this is smaller than 1, maybe I forgot, I think I forgot a constant. So it means that the identity minus gamma the gradient is gamma L divided by 2 averaged. But let me I think I should put a gamma here. So a gamma square here. Right? Yeah. Because this should be, let's say, identity minus gamma the gradient. If yes. So the usual way in which how you write it is this one. So if it's bigger than 0 and gamma is smaller than 2 over L, meaning that 2 over gamma L is bigger than 1, then this is gamma L divided by 2 averaged. So now I will state this is the main example, and this directly follow from the coercivity of the gradient. So this morning we wrote the 3 characterizations of Lipschitz continuity of the gradient. If you write the coercivity one, the third one, and you use you develop just that square, you get the inequality. And so with this, basically, if we are able now to prove that iterations, to prove what happens in the examples, that is that iterations of alpha averaged operators are convergent, we have for free convergence of the gradient method in the convex case for a Lipschitz, for a function with a Lipschitz continuous gradient. And that's what I want to do. So now I want to prove convergence of the iterates of fixed points, iterations of averaged operators. And so the results depend, the result depends basically on 2 preliminaries. The first one is just a consequence of, let's say, of being non-expansive. And the other one instead is the OPL lemma, which is used almost everywhere when you want to prove convergence of a first order method. So first one is this one, and it's called the demi-closeness principle. Save. So then the identity, so if T is a non-expansive operator, the identity minus T is demi-closed. What does it mean? Namely, if we have a sequence xk, which is weakly convergent to a point x, and we have that xk minus T of xk instead strongly converge to a point z, then necessarily x minus tx is equal to z. And so this is one of the points where the analysis in a finite dimensional space is slightly different from the analysis in an infinite dimensional one, in the sense that in finite dimension, you have a non-expansive operator, so the weak convergence is strong convergence, this is continuous, you have this for free. Instead here you have to prove it. And the proof, so I don't do it because it's just inequalities where you add and subtract things and you use the non-expansivity of T as, since it's the only assumptions that we made. So, so I would skip this. And so maybe, yes, it's a good point, since I forgot to point out some references for all of this. So basically, the analysis of first-order methods, there is a dichotomy in the analysis of first-order methods. There are the convex optimization, there is the convex optimization community, that is the French one, basically, that studies these kind of results. And so iterations of operators, even much more generality of that the one of minimization of convex functions, but to find fixed points in general of operators, or zeros, monotone inclusions, let's say. And I think that the best reference for this is this book by Bauschke and Combet. So there is a second edition, and it's called convex analysis or convex optimization and monotone operator theory. And then instead there is the other part of the word that most often is finite dimensional, and instead studies convergence of the function values. So the other point of view, and this is more related to the machine learning or I don't know, optimization, non-convex optimization community. And for this, there is a very good book by Nesterov, that is the one that I was mentioning this morning. And then there is a very accessible book by Boyd and Vandenberg. Yeah, maybe these ones. And then what I wanted to advertise, indeed, this was the reason why I was writing this too. There is, so you can find more or less all things that I was saying in a chapter by Salso and Villa. Maybe I should write them not capital. Close to this one should be like this. And but that is in a sense the most adherent to what I'm saying today. So that you can find the proofs that I'm skipping, for instance. Okay. So demi-closeness, right? Yeah.
Thank you. Just a quick recap, because I want to understand if I'm on point. So with the strictly convex functions, we are able to extract some results to our capabilities of converging to a minimum, thanks to the fact that they are somehow bounded by square functions. Is it a nice picture? Okay. So when we relax this, which are the functions we are somehow afraid of, in the sense, which are the functions which gives us problems? The one that are somehow indefinitely lowering their slope somehow?
Yeah, the problems, yes, here I think is a curvature problem. So you're afraid more on the flat
Okay, so
functions having
okay.
linear parts.
Okay. So very flat functions are the one that we're afraid. And using this trick, haven't we basically managed to escape from these problems and again be inside the realm of the somehow convergent operators, in the sense that yeah, exactly.
The alpha average.
Yeah, exactly. Why aren't you saying that every result I've already told you holds for operators like that?
Because it's not true. So we will see
okay.
that for these kind of operators, we will not be able to prove, for instance, strong convergence of the iterates toward a fixed point.
Okay.
So basically because it's not true.
Okay, so the alpha average.
The class is strictly bigger.
Okay. Okay, so there are some alpha average operators which are not contractions.
An example is exactly the identity minus gamma the gradient for a convex function.
Okay, so inside those operators, there are, for example, if my function is very flat, it might be that I will be stuck. Okay.
I don't know how, I don't have an idea to design to make a picture. So something, for instance, a function that grows linearly to infinity is not strongly convex. This cannot be strongly convex, for instance, something like this.
Okay, I see.
This function, identity minus gamma the gradient, is alpha average. So gamma L divided by 12.
Because if I start very far, I will be with the same velocity. Okay, thank you.
And yes, you can also have something like this. So we have to avoid the quadratic. Okay. Yeah. Okay. And the second, maybe, so this is the demi-closeness principle that will play a role. And the second result is the OPL lemma. So the OPL lemma is like this. So I take a subset of H, and I assume that is non-empty. Sure. And then that you have the following two properties. One, the first thing, every time you take a y in F, then this sequence is convergent. Not necessarily to 0, of course. So this is just convergence as a limit. And 2, every weak cluster point of xk is in F. Then what we can prove is that xk is weakly convergent to a point, let's call it x star, which is in F. So this is the replacement of the Banach-Cacciopoli fixed point theorem. Okay, so how do you do this? So the idea is to take two weak cluster points and then to prove that they must be equal. So I can say So I can say that these points exist in the sense that since the sequence xk is bounded, since I have the point 1, so I have convergence of xk minus y, so it is bounded. So it is, I can find two weak cluster points, maybe they are the same. And then what the trick is the following, to write this quantity. So x squared minus 2 y1 xk, and I do the same, so I should do this for everybody, y2. Okay, and now what do? I subtract these two inequalities. So this is equal to then this goes away. Okay. And now what can I say? I can say that y1 and since y1 and y2 are weak cluster points, they belong to F. So y1, y2 because this is the second assumption I was making. And then I can derive from 1 that these two quantities have a limit. So what I have is that at the end, so and so at the end, I can say that this is convergent, right? Because this is equal to this. If I pass to the limit, I have this minus this, which is convergence, minus these two that are constants. And this converges, therefore, to some beta. And now I use the fact that y1 and so y1 is a weak cluster point of xk. So if I take a suitable subsequence, this quantity should go to y1. So this on one hand should go to y1 minus y2. And on the other hand, this should go to, sorry, maybe let's write better. So this is y1 minus y2. And on the other hand, taking the other subsequence, this must be equal to y1 minus y2. So these quantities are equal. This means that y1 is equal to y2. So this sequence has a unique cluster point and belongs to F. Therefore, I have weak convergence to a point in F. Okay. Okay, so this is, I would say, the building block of the. So is everything clear? Are there questions? So we can write the Krasnoselski-Mann theorem. Yeah. I don't know. And so this is about convergence of iterations of alpha averaged operators. So T is an alpha averaged operator. I need to assume that the set of fixed points is non-empty. Then, so the defined is the fixed point iteration. So I write it so that we have it. X0 is arbitrary in H, and then xk plus 1 is T of xk. Okay. We defined as this, then 1. So then 2. So basically, I can prove these 3 results. So the first one, okay, is immediate and just tell me that the distance between 2 consecutive iterates is decreasing. And so as you can see, again, this is weaker than the one that I obtain when I have a contraction. And this is instead very useful when we will need to apply this to the gradient method or other first order things, and tell us that basically this quantity, so T of xk minus xk, is a square summable sequence. So I can upper bound this sum with something that depends on the constant of the alpha averageness constant and the distance of the initialization from the set of fixed points. So I should have stressed this also this morning. I'm sorry about that. But of course, when you have a convergence rate, you have the convergence rate, and then you have all the constants. And when you implement an algorithm, this is a critical constant. Of course, the quality of your initialization has an impact as a constant, so does not enter in the rate, but has an impact on the performance of your method. This is the same here. And the most interesting thing, I think, here maybe is the fact that we can have weak convergence of the iterates. So in general, there is no hope to strengthen this last result. So the convergence is weak, and you cannot hope to derive strong convergence in the general case, because there is a counterexample by Yon. So he has an example of a convex function in an infinite dimensional set space for which you have only weak convergence of the iterates, so strong convergence does not hold. Okay. Okay, so one, it's just the fact that this is this. So T is alpha average, so is non-expansive. Therefore, this is less or equal than xk minus 1. Okay. 2. So what should I do? So I should take, what do you call it? X So I start from a fixed point of t, and then I consider this distance. Okay, so this is exact. So since x is a fixed point of t, this is t of xk minus t of x. And therefore, I can use the alpha average definition, so the alpha averageness characterization. So I can write that this is less or equal than xk minus x squared minus 1 over alpha minus 1, identity minus t of xk minus identity minus t of x. This is just one of the characterizations of alpha averageness. Okay. And now what I have to note is the fact that x is a fixed point, so identity minus t of x is 0. And so what I get is that, so let me rearrange a bit. So this is all this quantity is, I can write it like this, txk minus, write it correctly, xk minus t of xk. Okay, so I take this on this side. What I get is that t of xk minus xk square, so is less or equal than here. So I have alpha divided 1 minus alpha. And what I have is xk minus x square minus, yeah, x minus xk plus 1 minus x square. Okay. And now here I have this telescopic, so I can sum on both sides. Here I have a telescopic sum, and then I derive that, I don't know, I exactly derive this. Okay, so maybe I do it, sorry. Okay, so what you get is that this sum so here, I keep just the first term, and I discard the second one, the last one, since it's negative. This is true for any x in the fixed points. And then I take the inf on the fixed points, and I get this inequality here. And finally, in order to prove weak convergence, I just need to prove that OPL lemma, the hypotheses of OPL lemma are satisfied. So I want to apply the previous lemma. So for 3, we need to prove so that 1 xk minus x is convergent for every x in the fixed points. So by assumption, this set is non-empty, so I don't have problems. And 2, every weak cluster point is a fixed point. So 1, the first one is easy because xk minus x is equal to t of xk minus t of x, since x is a fixed point, and this is less or equal, so this is exactly equal to, less or equal than x minus 1 minus x. So this sequence is decreasing, therefore is convergent second. So here I should use the demi-closeness principle. So assume that X is a weak cluster point, then I have a subsequence of xk which weakly converges to X. And what I can say is that, I don't rename it, okay, so that it's easy. This goes to 0, since this sequence is summable, okay? So necessarily, maybe I can keep it, it's the same. So this one goes to 0, okay? And therefore, by the demi-closeness principle, I have that when I replace this with X, the weak limit, this should be equal to 0. So Tx minus X is equal to 0. And therefore, X belongs to the fixed points of T. And therefore, Opial lemma holds, and I can derive weak convergence of the iterates. So in particular, this gives immediately convergence of the iterates of the gradient method in the convex setting under Lipschitz continuity of the gradient. So in this second part of the talk, I would like to start to go towards convex functions that are not necessarily differentiable, not necessarily smooth. And so we need some, let's say, convex analysis preliminaries. So I will be very limited. So I will introduce only the tools that I need, that I will use. So it will be a very small and partial introduction to the subject. And in particular, what we need is to find a surrogate, a replacement for the gradient, which we don't have anymore. And so what we will use is the subdifferential. So the setting, to be precise, the setting is the following. So we have a function. So in the convex optimization, f is defined on H and takes values in R and possibly plus infinity. And so what I will need is that this function is proper, in the sense that what is called the effective domain, that very often is then is denoted by dom f, is okay, non-empty. So basically, our function is not the function that is constantly plus infinity, which is not very interesting. So the setting is f proper, and then the second property that I need to ask is lowers my continuity. So we have seen it in the Augusto talk, I guess. So from the is very often this is also called closed, in the sense that you can characterize this as asking that the epigraph of the function, which is a thing that you use a lot in convex optimization. So you have your function, and then you can consider, sorry, this is not very convex. Oh, in any case, I don't care. So this is, I take a function. So, and the epigraph is the thing that is above the graph. And then in this, so if this set is closed, the function is lowers my continuous, and vice versa. If it's not, it's not. Okay. And so this is very often called closed by the optimization machine learning community. And that's it. So proper, closed, convex. So this class of functions is denoted by gamma 0. So, and this is the set where the things that I will say are true. So, right. So in this set, I define the subdifferential. at a point x. So in the domain. So let's write it and then we comment this. So this is the set of U in H such that f of y is bigger than f of x plus U times y minus x. And this is true for every y in H. So basically what you do when you define the subdifferential, you allow your function to be non-smooth, but you can still consider you try, let's say, to generalize the first order characterization of convex and smooth functions. And so you ask that your function is above some kind of linear function, which is, let's say, tangent at the point x. So the classical drawing that you see is the following one. Let's take the absolute value, which is non-differentiable at 0. And then here, so if I take a point, let's start here. If I take a point at this here, so for instance, what I get is that the only slope, the only line for which my function is above this green line everywhere is this one having slope 1, okay? And basically U here is the slope of the line. If instead I go to 0, then here, for instance, if I take this function, this line satisfies this inequality, okay, for every y. And I can find many others until I arrive here. Okay, so the set of all the slopes of these lines is the subdifferential at 0. So in general, the subdifferential is a set and is like that. So two properties that make this generalization useful. So this is called the convex there are many subdifferentials, many definitions of subdifferentials. This is the only one, I would say, in the convex setting. And the introduction was due to Moreau and Rockefeller. Okay, so this concept. And the subdifferential has two very good properties that are the following. First, if we have f in gamma 0, then is a tautology, I would say, that x star is a minimizer if and only if so let's say that the Fermat rule holds. So a minimizers are characterized as zeros of the subdifferential. So this seems a good generalization of gradient. And the second property, if we are in the interior of the domain of the function where I can compute the gradient, okay, so my function, if f is differentiable at x in the interior of the domain, then the subdifferential is equal to the gradient. So as I was, so this case is the standard one. So in points where your function is differentiable, the subdifferential is a singleton and coincides with the gradient. So in this sense, we will use this to replace the gradient. So just a couple of properties, and then I will define the first very natural algorithm that can be defined using the subdifferential. So what I will need in the future is just So what I need is that the subdifferential is nice in the sense that it has these two properties, but is less nice in the sense that when you need to compute, for instance, subdifferential of the sum, this is not always true. So you need to always remember to add some technical conditions that I have to say are very technical. The examples are quite pathological, but it may happen that the subgradient of the sum is not the sum of the subgradients. So I just write one case, which is a very simple one, is not the most general one, in which the sum rule holds. So I have f and g in gamma 0, and then I assume that there is an empty intersection between the domain of f and the interior of the domain of g. Then the subdifferential of the sum is really equal to the subdifferential of f plus the subdifferential of g. So they are really equal as mapping. So this inclusion is always true. Instead, to prove the other one, I need to impose some assumptions. So this is the only calculus rule that we will use. We will not use anything else. And so the other maybe the other thing that I want to write in order to give you, if you have never, is there anybody that sees the subdifferential for the first time? 1, 2, 3, 4, so many. Okay. So just to give you, this is a very quick introduction to the subdifferential, just to give you a sense of what it is. So the case is really the one, at least in R. So the case is really the one of the absolute value, in the sense that for real functions, you have a very simple characterization. So I write it informally because otherwise I have to add other things. So I take f in R, and so gamma 0 R. Then the subdifferential. Yes?
I'm sure it's a silly question, but what do you mean with the sum, like the proper vector?
The offsets.
Offsets. Ah, okay,
Yeah.
okay.
Yes. So all the possible sums for
okay.
U in the subdifferential and V in the subdifferential.
Okay. Thank you.
Yeah. No, thank you. So for functions in R, the situation is really the one of the absolute value, in the sense that you can always show that the derivative from the left of a convex function is smaller than the derivative from the right. And then the subdifferential is this one, is this interval intersected with R, in case these are infinite. So you can see, yeah. This is the subdifferential. So you compute the left derivative, the right derivative, and then you take the interval. And this is, as you can see, a closed convex set. This is always true, even in for every convex function. And if you are in the interior of the domain, then this is closed and bounded. And instead may be empty or unbounded when you are, it is empty or unbounded at the boundary of the domain. So just one additional thing, maybe nobody asked, but you may be curious of why we include plus infinity in these functions. And the idea is that you don't like constrained optimization, and you want to do unconstrained optimization. And so basically what you like to include in convex functions is what is called the indicator function of C. Closed and convex is this function. Which is a function that is 0 in C and plus infinity outside. So basically, when you add this indicator function to whatever function you have, and you consider, for instance, this problem, the problem of minimizing f plus the indicator function, then this is exactly the minimum for x in C of f of x. So basically, we will treat constrained optimization as unconstrained optimization problems. And this brings some, let's say, some difficulties in the sense that you have this plus infinity, that you may have these functions that are a proper domain. In particular, for instance, maybe we can compute the subdifferential, just write the subdifferential of the indicator. Let's assume that is closed and convex. Then, so I already write it here. I want to write this. What I should take is this u in H, such that, and then I have to write it. IC of y is bigger than IC of x plus u y minus x for every y in H. And then what I see is that, so I should be, so I usually, if I'm outside the domain, this doesn't make sense. So I should take x in the domain of the indicator, so x should be in C. And then the other thing that I see is that when x in C, this is 0. And then here I have this IC of y, and this is a meaningful, let's say, an informative inequality only when y itself is in C. So this means that this is the set of u in H such that u y minus x is less or equal than 0 for every y in C. And this is called, this is a name, and this is the what is called the normal cone to C at x. So this is most this is most interesting when you are at the boundary of C. So if you are here, for instance, we should take, so this is x, then I take y, and I must have that the scalar product between this vector for any y in C and my u is negative. Okay, so I should find a, this is more maybe here, so this should be like this, more or less. Okay, so here I should have a negative product with every vector y of the form y minus x. And this gives immediately, if you write it, this gives, for instance, the optimality condition for a constrained optimization problem, even smooth. If you start from F smooth, you find the optimality conditions. Okay. So with the subdifferential, the first thing that if we want to try to minimize a convex function, the first thing that comes to mind is to replace the gradient with the subdifferential. And so that's what I want to do now. Okay. Okay. And if we do this, we obtain an algorithm which is very much used in optimization, in machine learning. For instance, it is the base, I don't know if you know more or less the Pegasus method by Shalev-Schwarz, and I don't know. So it's a method which is used in practice. Even if the convergence theorem is, the convergence results are quite weak. So I forgot to say why it is called subgradient algorithm, since every element of the subdifferential is a subgradient, is called a subgradient. And so what you do in the subgradient algorithm is really the most natural thing we can try to do. So instead of doing xk minus gamma the gradient, we do xa minus gradient gamma gk with gk in the subdifferential of f at xk. So the first problem that is immediate is the fact that we need to have the subdifferential in order to derive, to define the problem, to define the algorithm. And so what is usually done is that the function f in this setting is as a full domain. In this way, the interior of the domain is the entire H, and we are ensured that we have a subdifferential. So I skipped this part, but you can say that the domain of the subdifferential contains the interior of the domain of F. So this solves this problem of having a candidate. So let's already try to list the good things of this algorithm. So GK is a subgradient, and this is good because you don't have to find one specific subgradient or to characterize the subdifferential, but it's enough to find one element. And usually computing the subdifferential is expensive, is difficult. So you know how to do it for special classes of functions, but in general it's not easy. So this is a good news. The bad news is that as I wrote it, it is not convergent. So the example is this one. So this does not converge. And the example is really, we can take the absolute value as an example. So if we take f of x equal to the absolute value of x, then, so what happens? So I start from at 0, which is different from 0. And what happens is that if I do, so maybe, yes, xk, I compute this difference, what I get is gamma absolute value of GK. So assume that I still not, I didn't hit 0, so I'm not at 0, xk is different from 0, then this GK necessarily is either a subgradient here, and then is 1, either a subgradient here, and then is -1. The absolute value is always 1, and so this is gamma. So I have that the distance between two consecutive iterates is strictly positive, and so there is no hope to have convergence. So this does not converge. So I will try doing like this, no? So something like this. And the problem is that the grade, so it doesn't become small when I go this. So how can we mitigate this problem? The classical way to do it is to choose the one that I saw at the beginning. You should never do it. A decreasing step size gamma k. Okay, it's the only way to make it convergent. So, and the other thing that, so now I write the convergence theorem. So I don't prove it since the proof is exactly the same as the stochastic case. And so we will prove the stochastic that we will see how it works. And the other thing that I wanted to say is that beyond this is really different from the gradient algorithm in the sense that, so we have not seen it yet, but the gradient method is a descent method, while this one is not. Or maybe, yes, we have seen it in the drawing, so it's fine. And this is not a descent direction. So the example is, for instance, this one. Let me see. So if you take this function, then so the sublevel sets are like this. So for instance, here is 1/2, 1. This is the one sublevel set. And then, okay, they are all like this. So let's choose this point 1, 0. Then if I compute the subdifferential at 1, 0, what do I get? So this is one, so, okay. Believe me, I will do, maybe if you want, I can write it there. So this is, so when you have a function which is the sum of independent variables, so here we have a function of x1 plus a function of x2. When you do the derivative, you derive with respect to x1, you derive with respect to x2. The same is true for the sub-differential. So here I can compute, this sub-differential will be a product, and will be the product of the sub-differential of this function at 1, so it will be 1, times the sub-differential of this, again, absolute value, this time at 0. So it is -1, 1 multiplied by 2. Okay? So when I take so if I put this set here, and I take minus the sub-differential, minus the subgradient, what I get are many things, but something like this, and then I go until 2, -2. So let's say all these directions, for instance, these two, are in the subdifferential and are not descent direction. As you can see, they don't go inside the sublevel set, but they push me away. And the same is true for many others until I arrive at this one. So all these ones are elements in the subdifferential that give not a descent direction. So it's not a matter of choosing a sufficiently small gamma, is that it does not exist a gamma for which minus gamma gk gives me a descent. So the analysis is different, and in particular, what is studied for these kind of algorithms is not the convergence of f of xk. This is not studied. When you have some algorithms like this that are not descending, you study something different, that is this stuff. So quantities of interest, let's say. And basically R2. The first one is this, I can call it fk, which is the minimum of f of xk. So I do k iterations. I'm not sure that my sequence will be a descending sequence, so I will not decrease f, and I take the best value I found so far until step k. The other quantity that is useful is this averaged sequence x bar k, which is sum gamma I xi divided by, so I0 to k divided by gamma k, and this gamma k is the sum of gamma I. So I average, I take a convex combinations of the iterates that depend on the step sizes that I chose. And what I can study, and the study is the same as this one, is f of x bar k. So this kind of f on the averaged sequence. So I can establish results on these two quantities. And so the result is like this. So theorem, convergence of subgradient method. Okay, so what I need to ask is, so I have an f, as I was saying before, should go to R, convex, and then I have to ask an additional assumption, which is very stringent, and that's why very often the subgradient descent is studied on bounded set, so indeed is a projected subgradient. So the point is that f is B Lipschitz. Then the following holds. And as usual, because I forgot, the set of minimizers is non-empty. Then, so 1. So I can prove this quantitative inequality. So, right. Okay. So this is true both for the best iterate and for the same for the average, the function on the average iterate. So basically what you prove is that you can upper bound this difference with the two terms. One, which let's say depends on the initialization. This is true for any R-min, for any point in the R-min. So I can put the distance. Okay, R-min F. And here I have the sum of the step sizes. And here instead, there is this term that if you want takes into account of that problem that I had before of the gamma minus gamma, that this subgradient do not vanish. And so we have the bound of this B square, which is the Lipschitz constant of F, and gives a bound for the for each subgradient. And this sum of the steps square divided by the sum. So in order to have convergence, I have to make this going to plus infinity and this quantity going to 0. And these are the classical assumptions on so if so the gamma k is the sum of gamma k goes to is plus infinity, and the simplest is let's assume this. So gamma k is in L2 but not in L1, then f of xk, fk converges towards the minimum of f. And you can also prove with convergence of the iterates. Okay. Okay. So once that we have this result, one can wonder what is the best choice for the step size. And so the best choice for the step size is a constant choice where gamma, but which requires the knowledge of the number of iterations. So if I know in advance that I will do k iterations, then the best possible choice I can make is to choose gamma I constant equal to 1 over square root of k plus 1. So now I forget this is what is called the finite horizon bounds. So you know exactly how many iterations you will do. If instead you don't know how many iterations you will do because you don't know exactly when you want to stop, then you can do an online choice, what is called an online choice, and the best choice is again 1 over square root of I plus 1. So what happens is that in this case, it's easy to derive that you get the convergence of 1 over square root of k. So the convergence rate for this quantity, then maybe I write it. So with fixed step size, then you get fk minus minimum of f, which is less than a constant divided by the square root of k plus 1. Instead, if you do the online choice, then what you get is that you should get fk minus minimum of f is something like a constant. Here you get square root, so something like this, logarithm. You get something like this. And these are the, let's say, usually it is said that subgradient converges 1 over square root of. Yeah.
So we saw the counterexample where we choose gamma I to be constant doesn't work, right? So
sorry, yes. Constant in the sense that this is true for iterate k. Then if you want to have convergence and you will do, I don't know, k plus 2 iterates, then you have to choose your gamma. You have to start from the beginning and choose your gamma as 1 over k plus 2. So it's not really, this is not an asymptotic result. Okay. It's always a finite time result. So at iterate k, you have that inequality with gamma, which is chosen as a function of k. I don't know if it's clear. Okay. Instead, if you want to have convergence, so this is, let's say, for fixed k, maybe it's good to write. And instead, if you want to have convergence, you have to choose the gamma i's decreasing, and you have this quantity that instead holds for every k. Okay. And so in practice, so this is a very bad, as I was saying, this is a very bad policy for the choice of the step size because you don't know what to do. So you will start, what you usually do is that you launch many algorithms with different steps until so you fine tune the step size. That's the point. And yes, and also this convergence rate is called sublinear. So we are in another world with respect to strong convexity. And so it, in general, it decreases as let's say, square root of k. And you have also the logarithm, but very often the logarithm, so you don't care, is small. And
so the counterexample case that this equality, right? Because in the mod x place, we saw that the distance is constant.
yeah, this distance is constant, so I will, and is of order of gamma. So at step k, I will have this distance. Okay. Okay, so I stop here, and so maybe just why this is relevant for machine learning, for minimizing SVM. So the one of the most famous learning setting in which this is one case which I didn't mention this morning, where the loss function is not differentiable. Okay, because the loss function is 1 minus t plus. So for this, you cannot use gradient descent. So for SVM, this is used. And Pegasus is an example. Questions? No? Yeah?
Very slow.
Thank you. But so if you know, if I have understood well, if you know the number of steps, it's also the first inequality. And if we don't know the number of steps, it's also the second.
Yes,
For,
yes,
okay.
yes.
Okay, thank you.
So other questions? Probably is a good time to finish this day. So let's thank Silvia again.